Hi, this is CodeWeaver. Welcome to my very first video blog, I guess, for computer programming. I'm a computer programmer, write software for a living. I decided that I'd like to do something on my own time that was sort of an exploration of languages and interesting features, styles of programming, cross-pollination between languages and styles, and some interesting puzzles, just whatever I happen to see fit. I have been doing a lot of live streaming of games. I don't do it as a day job. I just do it because it's fun. But I decided to try something different here. So let's see where we can go with this. This is the first time I've tried to live stream some code, so there's likely to be some hiccups as I figure out how to do this with all the windowing I have to do. I'm really operating off of one monitor. I really should hook up another, but that wouldn't help me organize the stream all that much. It just means I'd have to personally shift windows around less. Anyway, let's get right on into this. So today we are going to be looking at let's not go there, let's go to the problem description I have here, which is we're just going to do some Pythagorean triples today. Now this puzzle is a puzzle, is not super snazzy, but that's actually kind of the point. I wanted something that took at least a little bit of coding, but that wasn't super hard to understand in concept, because I wanted to do a little bit of a language comparison today. I'm going to be writing pretty much the same code, or at least the same kinds of solutions in both C++ and Haskell, including trying to write the style of one in the language of the other, just to explore and tease out some of the angles on this. Now, I've done this once or twice before in posts I've made to Facebook and the like, which has been kind of fun. Doing this live should be another quite interesting experience. This is not going to be some sort of crazy accelerated video. It's going to be done entirely live. So be prepared to skip ahead when you want to just take a look at the code I'm writing. But so I've got a couple of different variations here, and the reason why I'm doing this is because I want to look also a little bit at code reuse and how that might affect how you might write this code. But the basic idea is this very first one here. We have as an input an integer n, which indicates the maximum side length of a triangle. I should focus on the fact that it's an integer, because the output is an iterable container, just a collection of three tuples, basically a structure with three components in it, I guess, of lengths of sides a, b, and c of the triangle containing n such triples, such that a squared plus b squared equals c squared. So a right-angled triangle. Now, obviously, the very simplest one that you're going to find is 3, 4, 5. If that doesn't pop up almost immediately in our solution, we've done something terribly wrong. But there are, of course, others. And I should actually add one of the other constraints here, which I'll add in a second. But we want the list ordered by C, then B, then A, so that we can see the longest side being C, the hypotenuse, ordered by that, and then B being the next biggest one, and A being the smallest. Just as a convention. It doesn't really matter, of course, but that's what we're going to do. There is also one other thing here that I forgot to add to each of these constraints. So there we go. It's going to be that there is no common factor between A, B, and C. Triangle is not a multiple of a smaller triangle, is effectively what that's supposed to arrange. And the reason for that is it just adds a little bit of extra complexity to this. It also means that the triangles are unique. So there's probably some super impressive and clever ways to generate these, other than doing a semi-clever but hard search. I frankly don't know what they are. I'd love to hear what your opinion is on ways that we can improve this, but you'll see where I go with this. And again, this is mostly about comparison of programming styles, not about the most optimal way to solve this particular puzzle. Just putting that out there. So this is what we're going to try to do. Relatively simple description, because the puzzle isn't the point here. Not really. So, as a setup for this, of course, I have some test harness code here. I have basically a main, which is going to call a bunch of test functions. We're going to put some unit tests in here. as we want to just test some throwaway code just to test to make sure our functions are working. any larger primary tests that we want to do, and any time that involve making sure it's correct but on a much larger scale, and then some timed tests afterward. And we may not use all these sections. I just created this as a template. Let's just get rid of Mr. Hello World, because we really don't need that in there. That's a leftover from when I constructed the project. So the time tests, in this case, what we're going to be doing, I have a test function here just as a demo. This just adds together the first n integers, for which there's an explicit solution, but this is the hard, hard just add them all up solution. I'm using long longs here because the test case I have requires an integer that big. And the way I run it is basically just to call the function. I wrap it up in this lambda just so that I can submit it to my timing function, which tests the execution of it from before and after, and delivers me a number in seconds that is the timing of this function. So let's find out how this works, right? Let's do a build. And I think you can see, okay, so what we're going to do, we're actually going to hide the PowerShell window because we don't need that yet. We are going to turn that off. I'm sorry that that has distracted you until now, but we're doing this completely live, and I almost completely quoted a very, very terrible television personality. So let's go on to, I got to turn on the console. Right, so this should pop up the console window in OBS from Visual Studio, and it did not. Oh, yes, it did. Very good. I actually figured this out. So here's our time tests. That's the actual answer. 5 and a bunch of zeros, 5 and a bunch of zeros is the correct answer for some of the first integers, 1 plus 2 plus 3, all the way up to this big number. Well, I can't even figure out what that is. What is that? That's 100 million. 1 up to 100 million gives this result. And it was able to do it in 0.059 seconds. Now, this is large enough for me to time in my really simple timing mechanism. But of course, if system stuff happens in the middle, that's going to get caught in this. It's not a super clever way to do profiling. I'm just getting a high performance clock sample before and after running it, and subtracting it too. That's all I'm really doing in time it. So that's going to have some error bounds on it. I just didn't want to make the number super lots larger. It's an approximate value. It's probably out by 10 or 20% because it's that small. But let's take a look at, well, it's probably not that inaccurate, but anyway, if I ran it again, for example, you'd see a slightly different number. Yeah, see? So, out by a small bit each time, and you'll see that over and over and over again. And that's not terribly important. We're only going to get approximate and vague timing. It's just to see if something has gone horribly wrong. But it's kind of useful to know what's going on timing-wise. So, that is just to demonstrate an example of a very simple function that I can duplicate over on the Haskell side. Here's the Haskell version of that same function. We have basically, this is describing a function that takes an integer and returns an integer. I'm on a 64-bit system, so this is actually a 64-bit quantity, which corresponds to the other code. The SumFirst function takes one parameter. It then enumerates values from 0 to n, and I'll explain the syntax later. It's not really that important right now. This does a fold, which is basically to, in C++, it's the equivalent of the standard accumulate function that basically folds a collection of things into a growing blob, an accumulator of things. And in this case, it's doing that by way of plus. So it's got an accumulator, and it's just continually adding in each element with a starting seed value of 0. So this ends up doing 0 plus all of this. And it produces a value. And you can see that the function I've laid out here is pretty much the same. This is how Haskell does sort of, I guess you could say, impure stateful code. It's by doing stuff inside an IO marked block. I'm not really going to explain that because I'm not going to spend a lot of time doing IO related stuff. But when I have to do a sequence of things, or I have to do stuff where to give the illusion of mutation of state and the like from within, just for IO purposes, this is what this looks like. And you can see just a bunch of print statements, a little bit like what I have on the C++ side. Here is that equivalent line where I compute a value, I time its evaluation, and we'll go into the laziness of Haskell later. But this times the actual forcing of generating an actual value. And then I pull out both the value and the time here and then print it out. And so this looks pretty much exactly the same code, because the imperative part of this code is kind of really similar. So we're going to quickly pop over to the PowerShell window, and you can actually see the results of this, but I'm going to rerun it anyway. So here we go, Pythagorean triples. And it takes a few seconds to compile with all the optimizations on. And you can see we get a value of 0.045. Although that looks like it's a little bit faster than the C++, it's probably about comparable. At this, with this particular test, there's a lot of system stuff and startup stuff that gets in the way of both the C++ and Haskell versions of this, and merely shifting around a little bit of the code will actually cause the number in Haskell to rise, or the number in C++ to rise. So these are roughly comparable values. These languages and their respective compilers, the GHC compiler for Haskell, Visual Studio 2019 is my compiler choice, as you can see, for this particular vlog. So these are comparable enough that makes no difference, and so we're going to get on to solving the real problem. We're going to go into Pythagorean triples. Let's just make sure I can watch the chat room in case anybody pops in and says hi. I don't see anyone in there at the moment, and even my own stream view seems to have stalled. Isn't that just fantastic? Reconnecting to chat, checking the viewers. I just like monitoring my own stream just in case any problems come up. But anyway, let's get back into doing a little bit of code here. We're going to go into Pythagorean triples, and we're going to start on the C++ side. It bears saying at this point, so I'm going to turn off that because we're not going to need it yet. Turn back on the other console window when Visual Studio pops it up, and we are good to go. Why did I choose C++? I've been programming in it a long time. One of the first sort of medium level languages, high level languages, I guess you could call it, that does get down to the bare metal. I started learning C actually back in high school, and I moved on to C++, and I kind of never looked back, although I love what they're doing with modern C. Named fields in construction of structures, you gotta love it. For initialization, I wish they do that in C++. But anyway, the reason I use that's the reason I'm using C++ is because I've used C++ for a very long time, but I haven't lately at work. I use a lot of C# at work, doing a lot of work in Unity. I did some C++ when I was doing Unreal, but I'm using Unity right now at any rate. Lots of C#, perfectly good language. Just not the things that I want to explore are I think more fun to see in C++, even though C# has their equivalents. There's a lot of stuff in C# I wish C++ had, but the gap is closing as the language evolves, and I'm not going to go into that because it's a big language discussion. Let's get on with the actual code. Haskell I decided to use because it's pretty much the exact opposite of C++ in a lot of ways, and still gives extremely performant code. It's a functional language, but it's also one that has a really high performance compiler that generates pretty good quality code, and like at the assembly level. And so it's a good candidate for showing that a completely different style of language can be used to generate comparable code from a performance characteristic. So plus I like the language. Lots of people enjoy Scala and Clojure and the like. I have tried those and they are good. But this is what I've chosen. I also don't use C++ and Haskell in any of my work, and that's why I'm going with this. So let's start out. We're not actually going to need some first in anymore, but we're going to leave it in there just until we have more code to stick in here. So what we're going to want is we want to actually have a function that is going to almost literally be this signature. And I could use a list. I could use a straight array. I'm just going to use a vector because why not? It is an expandable array, but and I don't need to have it expand if I reserve the right amount of space. Actually, I'm not going to be able to. So that's an interesting point. Because of the way I've worded it, I don't actually know ahead of time how many triangles I will generate when the largest size is less than or equal to n. An integer which indicates the maximum side length. So the hypotenuse is going to get as big as n. Should probably call it h. But it's going to get as big as n. But I don't know how many triangles actually fit that bill. If I set n to be 1,000, there could be 30 triangles or 100 triangles in there, and I don't actually know up front. There might be an analytic way to do that. I'm not a mathematician. I just play one on TV. I don't even play one on TV. So we are going to have something that expands in some sense, even though we're never really going to be altering them after we build them up. So let's start with this and see where we go. So you know what I might actually do is I'm going to do this. I'm going to be using this tuple int absolutely everywhere. So we're going to start out by simplifying this down a little bit. We're going to call this using try equals tuple int, and we're going to do using tries equals vector try. And now we have a faster way to refer to these. And I am going to prefix this with this everywhere because I don't like using the namespace stuff all that much unless the code gets really stupidly long. So you'll have to forgive that affectation, but all that says is use the vector that's in the standard namespace. Right, which means that we can reduce this to that, which I like. Oh, and we're going to need standard tuple. Huzzah. So let's go with the really simplest version of this because that will enable us to make this more flexible, more complicated, but it enables us to do a really rapid fire tests of these kinds. So we're going to do PyList. We're going to actually we're going to break with the convention that I suggested up there in terms of name. We're going to call this PyList by nested loops because I'm going to want to name these, but you can just assume that all of these are PyList. They're just different versions of PyList. So we are going to say, and actually what we'll do so that we can no, we're going to leave that alone. We're going to start by writing a very, very simple for loop based mechanism for this. Why not, right? Keep in mind, I am well aware that C++ 20 has some delicious stuff going on with ranges, which for the C# aficionados is very close to being able to use link. It does sort of lazy evaluation of collections. I am not going to use that because I'm not familiar enough with them. I may revisit this at some point, or I may do a second video involving ranges where I start experimenting with that. So I will not get that complicated. I am totally fine with using the rest of the STL, however, as you can probably see. But let's start with the simple stuff. For so we're simply going to, actually what we're going to do is we're going to relabel these. So this is, so n is going to be the maximum size side, but that means that we can effectively do this, right? We're going to actually state what the size of C is. We are then going to, and this is going to be a dumb version of this, int b equals, well, we can't have 0. 0 is, we can't have a 0 size. I guess I should have probably put that as a constraint above, but triangles with any sides being 0 means you've got a degenerate triangle. And 0, 0, 0 is not a case that I'm interested in. So, and actually it has to be less than or equal to n, doesn't it? Less than or equal to n. B is less than or equal to Now, in order to satisfy the constraint that we have an ordered B, C, and A, B is always going to be less than or equal to C. In fact, it strictly has to be less than C, because if it were equal to C, then then A would definitely have to be 0. So we're not going to have that case either. So B is less than C plus B. So that's it. We're also going to do the inner loop, and I know we don't have to actually do this. I'm going to write a cleaner one in a minute. And the same property applies, except that A and B in principle could be the same, and you could probably figure out why that can never actually occur. But by the constraints that I've said above, this is a perfectly reasonable thing to ask. Are there any where this is to be the case? If you didn't know this from studying the math, you might actually try this. So we're going to do the dumbest possible version of this, which is to generate all of these relevant values. And we are going to ask the question, is this a right angle triangle? Is right angle try? And we might use this const try ampersand try. There we go. Is right angle. So a couple of things we can do here. Let's start with this, and we're going to say these are all integers. So if A times A plus B times B equals C times C, because we don't have a squaring operator in C++ or an exponentiation operator, and this is just the simplest way to do this, and it's actually try dot. Just going to do this the naive way and then refine it as we go, because why not? Mostly so that I can show the comparison. Oh, right, because this is a tuple. We don't actually have A, B, and C, do we? Okay, that's an interesting point. And hang on a second. I just got to pull open my... I am going to have to keep my laptop from falling asleep, or that's going to get really, really annoying having to wake it up every so often. So let's see if I can force disabling of the sleep mechanism. There we go. So we don't have an A, B, and C in here. We actually have 0, 1, and 2. So and the reason I'm using tuples is instead of structures is no reason at all that I can fathom, except that I called it a tuple in the description of the code. I could go and just make this a struct instead. A into B into C, and I'm not going to make this a class because for a couple of reasons. It doesn't really, well, I suppose I could. Because I'm never going to change it after I create it. And that is kind of consistent with the, too much time at work, writing in C#, where that is the way that you declare public variables. I could do it this way. But I kind of want to enforce the idea, at least in this code, that I'm not really mutating these after I generate them. And unfortunately, this implies that you can. So, all right. And I realized that I could still call it a struct in C++, because it doesn't really matter. It just controls the default public, private, protected. So, okay, fine. We will make these protected. Nobody else can see them. Oh, this is going overboard, but here we go. So we are going to do this. I'm going to call these. Don't usually write in this style, but I'm going to do it here anyway. So this is just going to make the code a little easier to read. I suppose I can do the same thing in Haskell. There's no reason why I can't. So try, are we going to allow creation of blank triangles? No, we are not. So we are going to, I think we can do that. We're going to take out that particular one, or at least guarantee that it doesn't exist. We are going to have one that takes we're going to take the right hand side, and then we're going to go MA equals right.MA. This is all going to be some boilerplate stuff. This is kind of why I've started to lose interest in writing full classes for what are essentially really simple data types. I'm starting to prefer to use structures, but I realize it might offend the sensibilities of all the object-oriented people who would rather I do a proper class, which actually really wouldn't stop me. But let's do it this way, actually, because of what I said. This would mimic the immutability properties that I want to share between these programs. I'm very big on immutability. I'm starting to do that in my C++ code as well, in certain styles of solutions. We're going to have right, and we're going to go more or less a duplicate of this. Hang on, actually, this is a very silly way to do this. I am forgetting my C++. It's another reason for me to do this in C++ is so that I can remind myself how to do this. Proper member initialization. Can't type today, apparently. See if I can't get myself more comfortable on my keyboard here. Yay! Why? Oh, because I need the colon, of course. Yay! All right. This is actually going to be very close to this because it's just going to be A, B, and C. Yay! So there we have our structure. But we're going to need to be able to look at these, read them at some point. So for the sake of looking at these from a read point of view, I'll just create some quick accessors here. And I'm just going to give them the names of the parameters like this. So you can just call them A, B, and C. So this is going to be return MA. Now we're going to make sure that these are const. And in fact, these should probably be const expr as well. And wait a minute, why is this complaining? It is not a non-static data member or base class of try. What have I done here? Nope, problem's gone away. It was just a temporary non-existent bug. So we're going to call it const, and we're going to call it B, C, MB, and MC. And yeah, and this is just so that we can store the thing and pull it out, and we can actually print it out to the screen. So we're also going to want an output statement for this, but we'll get to that in a second. Is there anything else I want to do here? I want to make, let's first of all right, so we can't access these like members. I kind of wish C++ had properties where you can do the variable and control the get and the set on those properties. I thought that was quite a neat mechanism. And this is going to be a class tuple has no member. That's because we do not want that anymore. Yes. And now we have expression must be a modifiable L value because why? Oh, because of this. There we go. So actually, we don't need an if here. Return that. Yay, I can still write code, sort of. All right. Well, sure, he's still out, but so this, by the way, is also technically okay. So this can be done on try by making this const expert, and the reason why we want to do that on as many things as we can is in C++17, or I think it's C++17 where that started to come in. No, probably a little bit earlier than that, but it got refined in C++17. Const expert indicates to the compiler that it can and should compile this at compile time if there's an opportunity to do so. I don't think it will actually take advantage of this in this code, but we're going to write that in there anyway. And in fact, all of this probably could be made const expert. We'll find out. Can we build this? Const expert cannot result in a constant expression. Because why? Because these guys are also not const expert, but they can be. And in fact, so can the triangles. This entire thing, we could get the compiler to use tries. We could get the compiler to generate tries at compile time if we needed to. Again, it's not something you need to worry too much about here. My only reason for adding it is because if it's not there, I'm going to be wondering to myself why I didn't. The code will compile completely fine without them for our purposes. Okay. Which probably means I shouldn't have added it to the video, but there you go. I think that enables us to create them. It enables us to view them. Especially because what we're going to do here is we're going to say, okay, so is right angle try. We're going to make a try out of these. We're going to say try. Nope. We're going to go auto try equals try. I prefer doing it this way so that I don't have the try here, and I like using the auto and then the type syntax over here. And this doesn't mean that this is some sort of magic unknown type. It just means that it's using type deduction in order to specify the type of try. And the type is deduced from the value that's on the right-hand side here. I tend to like this so that I'm not, in some cases, not duplicating both a constructor call, sorry, a type on the left and a constructor call on the right. Mostly a style thing. So this is trying to make myself use modern syntax as is at least appropriate and not confusing. So we're going to go try of A, B, and C, just like that. Now, I'll grant you what I could do. I'm not going to do what I could do. I'm going to do what I am doing. If I get going down tangential paths, I will never get to where I'm going. So we're just going to go if is right angle try. And we are going to want tries. Okay. So here's the thing. Do I bother doing that? No, I think what I'm going to do in this case, because I know I just want the default constructions to do that. I don't know if that's me being inconsistent or if I just like that as a simple declaration of the default object. I'm not sure. I'll have to think about that. I've been coding in C++ a lot recently, so to make up some decisions about that. But now we have a container, tries dot push back try, which is more or less just adding it to the end of an array. This happens to be a vector instead of a bare array. Plus, it auto expands. And then at the end, return tries. Now, it might compile. It probably will compile. There's a pretty good chance I can't make this const expert because of the vector. But let's see if it'll let me. No, it really can't. there may be ways to make that work. It's not super duper important for this. But I know that there is a pretty big push in the C++ community to make as many things, even containers where possible, const expert. So you can get the compiler to do more things. You can force it to think about how it might solve it before it ever gets into the code. Getting stuff to solve in compile time is totally awesome. All right. I mean, this in principle is our solution. And so let's just test it out. Let's literally test it out. So we have this timed thing here. We're actually going to, what we're going to do is we're going to do the opposite of what we've got here. We're going to actually comment this out. Let me take that out, take that out. We're only going to do, so this is actually all the way up at primary tests. We're not going to do time tests just yet. So that's out. We might do a unit test or two just in case. So let's do that. Okay. So here we're going to, now I could use a formal like testing suite for this kind of thing. Like in Haskell, I could use quick check, and in here I could, you know what, I don't even know what tool I'd use on the C++ side. Maybe there's an equivalent to quick check. I've never checked. I'm going to keep this really, really simple because I don't want to spend a lot of time doing this, and I'm not practiced at using formal test packages, and I'm not super big on writing unit tests is good, and I like having a suite of brain checks, but yeah, I'm just the kind of I don't know how to say this. I'm just not the kind of coder that wants to spend 15 weeks writing test cases for 3 days of real code. As long as I can get faster at it. But let's figure out what I can do that would make sense. So I want to test is right angle. So let's just test some known things here. So we're just going to quickly do something like this. Is right angle try 3, 4, 5. Let's try to make this a little bit general here. What I would like to do is be able to say something like this. Correctly identify as right angle. Sure. Else. Actually, this is why formal test procedures or formal test packages are a good idea, because then you can probably get away with writing less boilerplate. And actually, we want to, strictly speaking, assert that this is the case. So there's a cute little trick in C++ that enables us to do this. And C, I suppose. Oh, I'm going to need C assert in this, aren't I? Let's just pop back up to here. I have a love-hate relationship with unit tests, I guess. Right, so we're going to say... this is a terrible idea, but what I'm going to do is I'm going to reproduce this so that it double checks what I've done. Assert not. Assert is right angle, which is going to fail. Failed to identify right angle. For try 3, 4, 5. Problem is, if I keep reproducing these test cases like this, I am going to end up with a lot of boilerplate copying of stuff, and I'm going to miss something. I don't like that. So, but let's just run this and find out what happens, right? Yep, 3 or 4 is correctly identified as a right angle. All right. Let's try another one. Let's try 2, 5, 8. Right? And again, we're going to have this boilerplate problem, so we're going to have to solve this. God, this is everywhere. All right. So we have to actually reverse these cases. So we are going to do is not right triangle, is correctly identified as not a, falsely identified as not a right angle, failed to identify not a right angle for try 258. All right. Oh, what did I do here? Is right angle is correctly identified as not a right angle, so it actually ended up in here, and then the assert did not fire. It should be is not a right angle, and it said it is falsely identified as not a right angle. So our is right angle test is broken. Oh, it's because that should be. Well, that's why you write test cases. Lesson learned. Yeah, this is going great. So correctly identified is not a right angle. And so if we actually had a failure in that, let's, for example, have a case where we goofed. We're going to say, for example, we're going to say is right angle 258. Right. Now this should get us into the failure case and actually assert. And it did not. Why? It's falsely identified as a right angle, and then we want to assert now, isn't that interesting? I thought this would have worked because this should evaluate to false. And false and a string should still evaluate to false. So this is a trick I have normally used. Let's get rid of this bit for a moment and just try this. No, it actually kept running. So that's interesting. Why did my assert fail? Oh, this is interesting. I may not be able to use asserts for this for reasons that I can't adequately explain. Oh, because I'm running in release mode. Almost certainly because I'm running in release mode. So for the moment, let's run in debug mode, and then I'll run in release mode whenever I wish to do any performance evaluation, which is probably the smarter way to go anyway. Yeah, there we go. We got the assert. So that's fine. I often do this style where I don't assert right away. I actually do the test and then redo the test on the assert just so that I can get a message out to the console, because I don't know, I just got into that habit. In a couple of tools I'm using, it just became easier to identify these failures in a log. And in some of those cases, the asserts didn't end up coming out in those logs. So you'll have to forgive me that rather quirky style. But this trick is fairly common in C++ because a string evaluates to a non-zero test. And so this has no impact on the Boolean. So the only thing that matters is the test that you're doing. But then when the assert happens, it outputs the message after the ampersands, which helps to identify what the problem is. Very common trick. So that's pretty good, but I don't really like the fact that I have all this duplicated stuff. So I'm going to do something slightly different. I'm going to do try equals try 3, 4, 5. And I'd like to be able to do, and let's see if we can do this. We should be able to do this. The only thing is that we're not going to be able to stuff it into here without a lot more jiggery pokery. So what we're gonna sacrifice this, but it will enable us to do that, provided that we output try as a yes. I think this is the way we're gonna go. Do we really care about this? This is going to be a lot of work for not much benefit. And I want to get on to the actual coding of the Pythagorean triples. So we're just going to do this for now because this is basically unit test code that I don't care about. If I wanted to write something a little bit more formal, I could. Or I could use a proper checking tool. So we're just going to leave it at that. That tests a couple of the cases that we're interested in. We can add more. So there's our unit tests. Let's actually get to the point, though, of the primary test, which is to actually call this PyList by nested loops. Everybody can see how to improve this code. What am I doing here? Come on. Right. So we're going to do PyList by nested loops. So auto tries equals PyLoop by nested loops. And we're going to give it our, say, a small size test. So we're going to do small size, which we're going to have as a global constant because we're just going to rebuild this as we need it. We're not going to have a user interface on this because that's not the point of this either. Const x for const int bang equals, let's say 10. Let's find out if 10 is a good value for that. We'll call it small test size because that's a little bit more descriptive. Nobody viewing me, and that's okay. Because I actually didn't expect that. Auto tries equals pi. Okay, so that gives me the tries list, and then I'm going to want to say I'm going to want to do a test to make sure to do a double check that all of these are correct. But I could spend a lot of time like writing. I want to do a test to see that I've enforced the constraints above. So I suppose what I'm going to do is bool. So there's going to be tries by nested loops. I'm going to try to keep most of my functions from doing a lot of side effecty stuff. The fact that this, except for my unit tests, none of this stuff, I'm going to have most of my functions not actually do I/O, which means that my getting back a success value from this in this manner is not going to give me a lot of information, but if I need to change it later, I will. Analyze tries by nested loops, which I don't have written yet, but that's okay. And we're going to say if this, then okay, so this succeeded. Else. I'm going to have a lot of this kind of code in here, and I could, again, factor that out. I don't know how much I want to. Probably do. So let's figure out how I want to refactor this in a minute. So we're going to assert that this is still the case, which it's automatically going to fail. That's okay. And boink. What the hell am I doing? Don't need to do that. Right, there we go. So the problem is we don't have this. So let's write that. And we will write that up here. So this is going to take a list of tries. Lots of tries. It's going to return a bool. So here we go. Now we're going to, this is silly talk. We are going to avoid using for loops for this because we can. So what we're going to do, oh, we're going to at least use what is it, auto try in tries, and we can do const auto, const, and not only that, we can do const auto ref. I could do something with one of the standard algorithms, but that's just going to obscure this code. So if we find any failures, we're going to return false. Otherwise, at the end, we're going to return true. And so we're going to say, first of all, if not is, what is the name of that function? Is right angle. False. Furthermore, if is right angle, sorry, not is right angle, what am I doing? If try.a is greater than try.b, and try.b is greater than try.c, not or, not and, it's going to be or. Then also return false. Now, what were my constraints? Let's just double check my constraints here. The way I stated this is that A is less than or equal to B, and that should actually arguably be less than C, but let's actually put it this way. We want it ordered that way, but we also want that C is greater than 0. And actually, they should all be non-zero in principle because, so A, B, and C are non-zero. With that in mind, try A is equal to 0, or try B is equal to 0, or try C is equal to 0, then we return false. And I think for what we're going to want to do is we're going to want to output some number of these tries just to see. So what we're going to do is we're going to write a little thing called dump effective, dump example tries. This little thing is just going to dump to the console a portion of the triangles, because some of these are going to get very, very large. So what we're going to want to do, and this is going to be tries, try. There we go. Once again, we are going to do for auto blank ampersand try in tries. So we're going to do something like there's something like this. We're going to say see out, and my laptop has gone to sleep again even though I told it not to. I'm monitoring the stream on, so go figure, right? See out. So we want to be able to actually output some portion of these tries, so I actually don't really want to do it quite this way. What I want to do is I want to sort of get the first few at the beginning and the first few at the end, unless it's a particularly big collection. So let's do max size is equal max segment, I guess, is equal to 3. So what we're going to do is this. We're going to go try dot. We'll be able to take the first few and the last few as long as I don't end up. Okay, how do I want to do this? If try dot size, tries dot size is less than 2 times max segment. We're going to do basically, we're just going to basically output all of them. We don't have something that can actually do outputting of try yet, but we will get to that in a second too. We are also then going to say else. We're actually going to do this in 2 stages for max segment and actually I'm going to do that. Probably find a way to do this a little bit more cleverly, especially using ranges later, but I could also probably do this a bit smarter using, I wonder what I could do that would be more C++-esque rather than just monkeying around with arrays, vectors as if they were arrays. You know what, it's not worth my time to do that on the stream now. I can do that as part of I'm getting clever with STL later. So tries I. And then what we're going to do is we're going to go I is equal to, actually this should be size T now that I come to think of it. Okay, so this is going to equal tries.size minus max segment minus 1. No, size minus max segment. I think that's correct. I is less than tries.size. Correct. Okay, and then we are going to go after outputting. So what this is going to do is output the first 3 and the last 3, and in the middle. So what we've got here is something that can basically dump out for us blocks of tries. Oops. Yeah. My apologies to Jason Turner, incidentally, wonderful YouTuber on C++ related things. Really doesn't like using standard endl in the middle of code like this because of performance reasons. But you know, there's an argument to be made, but I'm going to do it anyway because I'm used to it, and this is not a performance bit of code. So yeah, go see his videos. He's really awesome. All right, so dump example tries, and this is complaining because tries is not identified because it's tries by nested loops. But now we have the problem that we don't have a not overloaded operator in order to be able to use this as part of streaming. So let's go and do that. We are going to do this. We are going to do right. Standard stream reference operator less than std ostream out const try reference try, return out at the end, and in the meantime out. And I'm just going to output it without that try prefix in the front of it. I think I can get away with that. You all know I'm using a try structure. What I would normally do, I really like what I've recently started learning Python for other work-related stuff, and I really like the difference between the REPR string representation and the I can't remember what the other one is, the pretty printed version. I like the fact that one of them sort of outputs something that you could in principle reconstruct the type with, and the other one is just sort of a pretty version. I'm going to just output a tuple as a parenthesized list of items. You all know what that means in pretty much any language that is pseudocode, so it's just a tuple. That's all it means here. And it's just going to be, I think, more universal, because I'll do that on the Haskell side as well. I guess the default on the Haskell side, actually. So we're going to do out.a is not what I wanted, because I want try.a because I'm ridiculous. Try.b, try.c, and then closing parenthesis just to make it pretty. Ba-ding! All right, how are we doing? Doesn't mean it runs, but you know, we're here. So, well, let's just give it a run. Oh, but before I do that, I'm going to make sure that my that my laptop is open and that my stream is going and that I can see that everything is working okay. The stream has kind of crashed because, or not the stream itself, but my connection to it. Let's make sure OBS is still running, because that would be embarrassing. No, OBS is still running, but because my laptop went to sleep, my connection to my own stream has gotten a little bit hinky. But there we go. I think we're okay. I can see what we're doing here, and I'm going to hit the run button. And what do we have here? So we haven't quite got there, because what we've got here, a small test size, has only gotten 2 of them, but the second one is a duplicate of the first. And I have an extra return in the output, which I don't want. And so this doesn't quite solve the problem, because I don't have that filter on no multiples. But we are getting there, because 3, 4, 5, and 6, 8, 10 are perfectly legitimate versions of that. It's perfectly legitimate triangles, with the exception of the fact that one is a multiple of another. So we are going to, so dump example tries. So hang on a second. What do we want to do here? Okay, how do I get rid of that extra return in the output? That's because I put a standard endl out here. That's not what I want to do in any individual triangle, so that fixes the output problem. So now what we're after is, we are after We are after fixing the filtering problem. So we're going to go right back in here and make this work. So we're going to do is right angle try, and then we're going to say we also need to have and is lowest and not has common factor and we're going to pass in a number of values in order to be able to evaluate whether or not it has a common factor. And how do we want to submit those? I want that to not really care about the fact that it's coming from a triangle. I would prefer. So I'm going to do has common factor A, B, C. We don't need to pull them out of the triangle proper. We can just cheat and grab the values out of the variables that we've already got iterating here. Has common factor. Do we care about making this super general? You know what? My answer to that is at present no, because we're not going to be reusing this in other code. How would I write that? It's an interesting question. There's a couple of ways that I could do this. Let's start with passing in these individual values like this is not really going to be all that much different than passing in the triangle itself. Except that I'll pass the triangle in by reference. You could argue that that's a performance thing. I'm not going to worry about performance. Premature performance is a bit of a fool's errand. We should try to make sure that it is correct before we try to make it fast. So we're going to try to figure out, does this have a common factor? And we are going to, how would I like to do this? I am going to want this in array. I'm going to try to make this general. I'm going to want this in array form anyway. So let's just, I don't want to create a full vector out of it. Because that does come with potential heap complications. So bool has common factor. Okay. So we are going to want to, so there's going to be const expr. Let's just make this we're just going to do it this way. And the reason we're going to do it this way is because it's simple and it's not going to get super elaborate with all sorts of weird templating or throwing it into an array, which I could totally do, but this is premature optimization. Don't do it. Okay. The simplest way to do this is we need effectively to work out a divisor, any divisor that divides all of them. And I think what we can do is we can do this. There's a reasonably efficient way to get the greatest common divisor out of. We need a greatest common divisor out of 3 items, or a common divisor out of 3 items. I am not actually sure what the best way to do that is, and so what I'm going to do is I'm going to cheat common divisor of multiple numbers. Greatest common divisor is also called the greatest common factor. 2 numbers is the largest number that divides them both. Euclidean algorithm GCD with multiple numbers. So yeah, since GCD, greatest common divisor, is associative, GCD ABCD is the same as GCD of A, B, C, and then D. So, and then they go and talk about Python's reduce. And I really should read that in order to study Python's reduce. But we are going to use, we're going to come with GCD. Right, because I've done this code before. I just haven't applied it to multiple numbers, and I had forgotten that GCD was associative. Right. Now I just have to get the GCD code correct. And again, since this isn't really the point of the problem, I'm going to cheat and pull out someone else's definition of GCD. Greatest common divisor, pseudocode, the Euclidean algorithm, which there is almost certainly a code example in here. I could work it out from first principles, but it's on a stream and I don't want to muck this up. So the GCD of A and B comes down to basically if B is equal to 0, then return A, else return, I could do this, is this recursion going to cause me problems? Probably not. It should optimize this away. And if it doesn't, it's a source of an optimization pass that we can make later. But from a recursively defining point of view, this is really, really lovely. A mod B. So, there we go. Having done that, has common factor, A, B, and C. So basically what we want is auto GCD equals, actually auto up several of these, but I won't. So GCD AB is equal to exactly what it says, GCD AB, auto GCD ABC is equal to GCD ABC if GCD ABC so actually return GCD ABC let's just fix that, is not equal to 1. And this does assume all of those values are not 0, but we already make that assumption. If we like, just as a super careful safety measure, we're going to have A is not equal to 0. And actually, we can actually put this assert up in here, just because this is where the actual problem will occur. GCD asked to, given A equals 0 parameter. Not going to get more complicated than that, but what this does mean is we should now have a working program. Oops, let's just fix that font size. There we go. In principle, I have not tested that GCD code. We should test that GCD code. Let's just run it and find out what happens. We have an assert because explosion. We got a given a B equals 0 parameter. Okay, so we have failed somewhere. We have failed because because B could be 0, because it's recursively calling itself. Yeah, so we can't do that. So we are going to have to do this at this layer where it's not recursive, or we have to make this not recursive, but A can never be 0. So we're going to do that. And we're actually going to do this. I probably won't be this diligent about asserts over on the Haskell side. We'll have to see. All right, 3, 4, 5 is the only one that we find. But it does in fact work. But I think we're going to want to make our small test a little bit larger. We want more than 2 items. So what we actually want is say, so we're going to set this up to say, I don't know, 50 and see what happens. This is going to take a little bit longer to, well, not that much longer to run. Now that did come up with more than what we suspected was going to be the list. And so what we are going to do with that is we are going to do 2 things. Okay, so we're going to lower that down to 40. I just want to get it small enough. There we go. Small enough that we get all 6 items out of it. There are only 6 in principle. And those are the ones that are not multiples of a smaller one and that fit the criteria. So here's a working program. How does that suit you? This is not really I mean, it's adequately fast for small numbers. We're going to try to make it a little faster later on. But again, this isn't so much about the performance, and it's certainly also not about finding the optimal algorithm for generating Pythagorean triples. I may do that as an additional video where we just take one of these languages and see how far we can push this, maybe. But what I want to do now is go over onto the Haskell side and get this code coming out. All right, so we're going to do the same thing over on the Haskell side. And I'm going to take a 2-second break and have a sip of water. Huzzah! Now, the one thing that I'm a little worried about, though, is we don't have a unit test for the GCD stuff. I'd really like to prove that it works, but I have. I'm going to not do that because it will be a lot of extra code for not much benefit, given that I basically pulled the GCD stuff off of Wikipedia and that associativity comment. That associativity comment basically nails it. So as long as I'm reasonably confident in the code, I can leave it alone. I'm okay for the moment on that. So PyList by nested loops, by the way, succeeded. We have all of them being correctly tries, all of them in the correct order. And actually what I should do is add one more thing to my validity test, and that's that I got them sorted in the right order. So what we're going to do is we're going to have to add one more thing to our test case. I suspect this is going to go into a part 2 and a part 3, because once I get this working in both, I'm going to start refining it in both languages. So let's ignore the unit test for the moment. Dump example tries. No, analyze tries is what I want to do. So what I want to do is I want to look at each try with respect to its neighbor. And so I'm going to rewrite this slightly because I'd like to do this in one pass if possible. Fail now, fail early. So instead of doing this style of loop, I'm going to do I could refine this later. Premature optimization is a fool's game. Let's just do the simple thing, because this is just a bit of test code anyway. Let's... All right, we're going to do... Yeah. What I want to do is I want to look at each one and the one that it's adjacent to. So we're going to do this. We're going to do auto I is equal to tries dot begin. We're going to use iterators because we aren't using ranges and we can't do it in, that way. And I don't. And I think I want to keep this. from getting too STL heavy at the start, except that this is just an iterator. It's not really any different than using an index. I just don't want to use an explicit numerical index when I can avoid doing so. So for equals I dot okay, I actually want it to be effectively I plus 1. I don't want to write it in a sense that it's a vector. I know I can do numerical addition. I can do arbitrary addition to the iterators, so I guess I might as well. I would prefer to. I've gotten so used to writing in Haskell where I don't have random access into stuff a lot of the time. So I tend to write often in a style where I would just start at I and just then go ahead through an auto increment rather than adding an explicit one. But that just makes life a little more complicated. So j is not equal to tries.end. So we're going to increase I and we're going to increase j. And I would love to do multiple initialization in the fors. I don't think I can do that, but the language changing as it is, that may not be the case. I will have to check that out eventually. Oh, no, I just got spam in my chat. Yay, spam. I love spam. No, I don't. So that, however, is not going to work if there's nothing in this. So I kind of want to say analyze tries. I want to have a case here where if tries dot empty, then just return true. When I have 0 tries, I will say that all the tries in that set of 0 pass, and we're good. What that means is that I can guarantee there's at least one, which means that this is a valid element. And when this gets initialized, even if there's only one element, that will be effectively tries.end, and then the loop will fall through. So what I'm now going to do, because now I and j point to adjacent elements, and it's just going to iterate through the array correctly and get to the end, I'm going to say if j c is greater than so I is the earlier one. So if IC is greater than JC, or if or if they're equal, so I need an extra case here. I could break this up into multiple if statements, but I'm not gonna. So I need specifically the case where these are equal, and this is going to be hard to read on one line. So let's not do that. I have changed my mind. That's just going to get horrible. Then, okay, so if that's the case, then return false. That's a fail case. If this is basically testing the ordering of the arrays. So if IC is equal to JC and then I'm going to go into this case and say if IB is greater than JB, this is the return false case. These are nested, and I can find different ways to express this that don't nest it in quite this way. But again, I'm not going to. I'm going to keep it simple. Else, because I don't technically need the else because I got an explicit return in there. If J if IB is equal to JB, return false. No, not return false. What am I doing? This is the inner case, finally, if I, A, is greater than J, A. That's when we want to return false. Right. Now, the case, for example, where C is less than JC, then neither B nor C even matter, and it will fall through and be true. So the only cases that are relevant is when IC is greater than JC, at which point it's immediately a fail. Or they could be equal, but then we have to go and test the B components. And then that chain of reasoning daisy chains down between B and A. And so this is what you do when you have multiple component comparisons, right? This is very similar to, say, if you were doing a sort operation on employee records and you were sorting by name, but for equal names you were sorting by, postal code or something, in order to be able to give a sorted list with multiple comparison points. So that should be another possible fail case. And let's just use the debugger just very briefly to make sure that we're even getting in here. Now, I'll note that I don't have a complex debugger on the Haskell side, so you're going to have to trust me to debug it that in a slightly different way. But we have the debugger here, so why not use it, right? So as we can see, as we're stepping through the tries list, that's actually not where I want to set the breakpoint. I actually want to set the breakpoint here. So looking in the watch window, looking at what this says, and you're not going to be able to read this very easily on the stream, but you can see that out of the first pair we're okay, and out of the second pair we're okay, and out of the third pair we're okay. And are we getting into each of the cases? So we're going to want to see if we're never going to get into that case, hopefully. And if we do, it's going to report a failure. But let's just put breakpoints in here. We know that we're getting through the loop, so we know it's falling past this case, but is it ever getting into this case? Let's find out. No, it actually never gets into that case. So there's no case that we have where there are two equivalent C's, but there's different B's and A's. And if you think about it, that makes kind of sense, because actually that may not be the case. Could it be that the sum of two different squares gives the same result? And I suspect you could actually prove that analytically. I can even think of a way that I might be able to prove it. But you know what? It doesn't matter. This is code that will catch that case if it ever happens. And so this may be overkill from the point of view that we could probably prove that some of these tests aren't necessary. But I put this test in this explicitly, and if it ever hits a false case, we will find out about it forthwith. And in any case, it's probably never gonna execute. It's probably never going to execute any of this code internally here at all, which means it could make the testing slightly faster, but I don't really care about that. So let's just run this and see what we get. So here is the result of this code, and I think this is now complete from the C++ side for this naive triple loop that simply does the hard three iterator search. And so this is gross. This is like I guess an n-cubed algorithm probably, but for small numbers of n, this is not going to kill us. Let us, though, just for giggles, because now this is easy for us to set up. We are going to, those are the unit tests, don't care about that. We're going to do this. We're going to duplicate this, but we're going to do tries by nested loops. So how do we want to do this in a way that I can possibly reuse variable names? Because I don't want to create 2 and 3 and 4 and 5 and whatever, because that's going to be a bit of a problem. So we're going to do that. All this does is add additional scoping, artificial scoping, so that all of my internal variables just go away. So that this means I can duplicate this, but now I can use in here big test size. And all the rest of the code just stays the same. But big test size is not defined. So let's sort that out, shall we? Here we go. So let's say we do 1,000, because that is going to be at least a little bit scary. Let's find out. And now it has stalled trying to do that work, because that is a very big number of tests to run. It is in debug mode, though, so we could improve the performance by, see, it did finish. And the reason being is we're not really doing 1,000 by 1,000 by 1,000, because when C is, for example, 200, then B will never go above 200, and A will never go above 200 because it never goes above B. And so, you know what? I'd have to actually do the big O to find out if that really is an O n cubed operation. But we're not going to be able to go much bigger than 1,000 without this becoming a problem. Like, I don't think we can go another factor of 10 without causing some grief. And that's fast enough. Well, let's find out. Let's... that is really lovely to look at, actually. So let's actually do a quick little verification here. I'm going to pull out a calculator, which you're not going to be able to see because reasons. So I just don't have the calculator up in OBS set up. So we're going to try this out. 372 times 372 plus 925 times 925. Oh, that is not correct. That did not work at all because I have typed the wrong operators. 372 times 372 plus 925 times 925 equals 994,009. And if I divide that by 997, I get 997, which is effectively that last number. So that proves that that last one is in fact correct. Try. Now, of course, we had the test case, or the test code. The checking code automatically determined that was the case. But I just wanted to verify it by hand. So those are the ones that we see. And actually, if I pull up a list... so I invite you to do the same thing here. If I go onto the web and say Pythagorean triples list, there we go. So what can we pull up? What can we actually get out of this? I ended up on Math World. First, let me see. Hypotenuses for which there exist distinct integer triangles. I'm not finding a distinct list of Pythagorean. I really, really want. Come on. Give me a better list here. So there is. Only 16 are primitive triplets with hypotenuse less than 100. 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25. And it goes on and lists quite a few. Now, I went up to 1,000 here, but I need to actually get... I need this ordered by ordered hypotenuse numbers. Squares are sums of two distinct non-zero squares. 5, 10, 13. Except that 10 is a duplicate and they're not unique. I'd like to find one that shows the uniques. And that's going to be tougher to find. But I can. So verifying these is going to be a little tricky because a lot of the lists don't list only the unique ones. It actually they actually show the duplicates as well, and I filtered those out. But what we can see here is that of these, I've got as far as I know all the ones less than 1,000 for the hypotenuse, and I've gotten all the ones that are unique because I've done a test to make sure that that is the case. And the test actually passes. Let's just run this in release very quickly to find out how fast that actually runs. Hang on a second. Just want to pop back over into Okay, and in fact, the slightly frightening thing is the release runs so fast. Let me see, can I actually do debug start without debugging? What happens if I do that? Does it actually pop up on screen? Yes, it does. It runs so fast that it literally blinks onto the screen. And so that just shows you the performance difference between release and debug. So for release, we could actually crank this up quite a bit. Let's actually go to 10,000 on release and actually see if that causes my computer to strain. So start without debugging. It'll do a quick rebuild. Yes, 10,000 does, because this is a rather expensive operation. I'm not even sure if that's going to finish, but let's let that run for a couple of minutes while I start talking about the Haskell version. So got a lot of work to do to get a comparable program here. So this is definitely going to be a multi-part series, I think, because I want to explore various ways of solving this problem. Going over to Pythagorean triples in the Haskell side of things. Oh, and you actually can't see the release that I ran in that fashion. That's unfortunate. Okay. I will tell you what the results of that are. Actually, can I just stall this and restart it in... It is not showing up in OBS. That is really frustrating. If I go back to debug... I am not entirely sure why OBS has decided to bail on the It's not OBS's fault. This is Visual Studio actually giving a different name to the window, and now OBS can't find it. That's incredibly frustrating. And I don't know how to fix that in any way other than to do this. So there we go. That's back on screen. I don't know why it renamed the window on me, and I don't care. I'm going to leave that running in the background. I'm not going to see it, but you will. At least you're going to see if it ever completes. And actually, I'm going to shut that down, and then I'm going to restart it, start without debugging. And the reason I'm going to do it that way is because I don't want it to shut down if I accidentally hit a button in Visual Studio. It's running independently, and we'll see if that ever gets anywhere. So now we're going to go and focus on the Haskell version of this, and I'll try not to let that console window get in the way of anything. In fact, can I tell OBS temporarily to slide that guy slightly off screen? Because you're not going to want to be able, you're not going to need to see it all the time. So small loop test succeeded. Let's go and do the Haskell version. at long last. So we're not going to need this again. And in fact, do I care about this? No, we're just going to get rid of this. It's in the way. We're going to uncomment that just like the C++ version. Now we don't have a complicated or a powerful debugger at our disposal other than the GHC's potentially built-in debugger, just like GDB has one. And so we're going to have to do this the old-fashioned way with hacked-up print statements, and you'll find out how I do that. Hopefully it won't take a lot of that. But we haven't done a whole lot of step debugging anyway, and I don't anticipate that's going to change. Let's just make sure that this compiles. And don't know if I can start showing you this at the same time as that console window. Let's figure out how we can do this. We are going to go into OBS, and we're going to put that up at the top here so that you can keep seeing it. But now we're going to turn on this guy. All right, here we go. We do not have time tests IO, right, because we need to comment that out because we're not doing time tests yet. Right. And we build and we build and we build. Hello, additional viewer. I don't know if you're still there. Feel free to say hi in the chat room. You don't have to. I'm just coding for fun, largely. Right, so, well, and educating myself and educating others, maybe. So, so we just run the equivalent code, and all I have is a do something because we don't actually have anything being done yet. So now we have to start doing the translation of the code. And we're going to start basically by doing what we should have done right at the beginning of the C++ version, which is define the structure. So we are going to do that. We are going to say, it's been a while since I've done this, data try equals, and let's see, oh boy, it has been a while, gee. Right, so the version of try is going to have a try constructor, and we are going to give it named fields. So basically this is going to be see if I can get this right. Right, so there's a try. Now in Haskell, data is immutable. And more to the point, not only is it immutable, but it also implies effectively that the values that you have in them can be synonymous with the accessors of them, because once you set them, that's it. You just set them. Now that works out well for our kind of program. We don't have to do anything clever with mutation over on the C++ side. We didn't have to do that in the C++ side. We just made a try and then we operated on the values. So what we are going to do is we are going to just leave that alone, but we do have to have the ability to print this thing. So we're going to basically allow this to print out by doing something like deriving. We'll use the automatic deriving. Now what this does, provided this compiles, is this automatically makes try a part of the show class, which goes and gives you sort of a from a Python point of view, it's the repr version of printing. It turns it into a string that you can then print, which you can use to reconstruct the object in principle. I'm not going to write the show class for this until I absolutely need to, because having it automatically do it for me is actually super, super helpful. Although it won't print out the same way as it won't print out quite the same way as the C++ version is until I actually write the common show. Now, can I, or the show that I want for it, can I run the GHCI version of this? Yes, and this gives me a REPL, right? So there we go. We have access to our types. So GHC has a REPL called GHCI, which is a command line interpreter, which enables you to basically run any of your scripts right in the interpreter. It does have some very slight differences from the compiled version, but and in some cases, some kinds of programs don't work well in the REPL, like stuff that's very heavily GUI based and the like. Or timing based or whatever, but for our purposes, it does enable us to write this thing before compiling and just run it. For example, I can run, I believe, main just like this, and there we go. So I'm going to use the REPL a bit until I'm ready to actually compile this for performance running. It helps me out a little bit. Let me see, let me make sure that the stream has that. Yes, okay. So let's start doing this conversion. Let's make sure that we can actually create a try. So try. I think we can do try 1, 2, 3, and that actually just makes us a try. And the evaluation of that as an expression is just literally the structure. But unfortunately, that doesn't let us sort of label things. So another way to do this is try just making pretty the syntax: A equals 1, B equals 2, C equals 3. And that gives us the same thing. And that enables us to use named initialization of the fields, a little bit like the modern versions of C does. Which I quite like, and C# does as well, so that's pretty cool. And that's all we really need. But you can see that the printout of this, so if the printout of the type, the effective ability to show it on the screen is controlled by the driving show. And so its output is going to look a little different than I strictly want. But I will fix that in a bit. I'd rather get the actual working code for this. So let's start by... so that replaces all of that, which is nice. And for my case, it's just convenient that it happens to collapse that down for me. I don't really need that, so let's just get rid of that. That's just a distraction at this point. And that's on the C++ side. Sorry, doing a little bit of impromptu cleanup here. We're going to get rid of that as well, so that doesn't impact us if we uncomment that. Let's talk about, so that'll be the equivalent of doing our own custom show operation. We want to have, now, so here's the thing. In Haskell, a very large amount of the work that we do is done in lists. A little bit like small talk, for example, or Clojure, which is, sorry, not small talk, Lisp. And a little bit like Clojure, which is sort of a Lisp derivative that is sort of a more functional style that interfaces with the Java runtime, which is really cool. But for our purposes, the reason we use it is because it's sort of a really simple way to use immutable collections that can nonetheless be sort of spliced and pulled apart and so on and so forth, which you'll see in a moment. Haskell does have various versions on arrays and fast vectors and the like, and we're not going to go there yet because, again, premature optimization is a bad idea. So we are going to do this in a very list-like Haskell-y way and then improve things as we go. But one of the nice things is that because lists are so extremely homogeneous but generic lists, in Haskell are so much a core part of the language. They're also a core part of the compiler, and so it does an enormous amount of optimizations. For example, actually, let's just go back here. If I just undo this for a second, this is actually just go all the way back. This sum first stuff that we have here, ignore this. This sum first stuff that we have here. This is all operating on lists. This actually enum_from_to produces a list, and this actually consumes a list. And Haskell is very, very good about fusing the operations on lists, so that in the end, this, although all the types and the intermediate types in this are lists, none of that makes it to the final assembler at all. And that's why you saw the timing that you did originally, is because it just fused all the lists away. They just vanished. And it can do that in a wide number of cases, and where it doesn't, you then go and do your optimization. That's why premature optimization is a really, really bad idea, because the compiler in Haskell is extremely clever, operating even on basic lists. And where you need it, you can do array operations and the like. You can even do mutations if you absolutely have to, and let's not, because it makes the code gross. Because this isn't a question of performance right now. So here we go. I am blathering. I'm blathering. So we're going to want some constant integers just like we have here. Let's just actually copy that straight over. And of course, this isn't actually how we declare this. We actually do it this way. Hang on. We actually say that this... we're going to make it explicit that this is an int, but we're not going to do that yet. So here's the problem. Haskell does have space-based blocking. You don't have to use it all the time. In fact, a lot of the times you can use brace-based stuff. I don't, because I have no problems with space-based blocking. You can see that I do a little bit of that down here. So if that bugs you, tough beans. It doesn't bug me because I just got used to it. Of course, Python also uses it too. And when I had to start learning Python this year, it didn't bother me there either. You just deal. So, however, the other thing that it has is case sensitivity on stuff. Which makes a lot of the code very uniform to read, actually. So classes like this, and classes, they're not classes like in C++, they're more like categories. You could call them interfaces from the point of view of a C++, C#, Java kind of thing, but they're a little bit more than interfaces, and we'll talk about that later. But call this a category is a bad word for a completely different reason, but it is basically a classification of this type to give it the properties of show. So interface for us, object-oriented C++ and cousin language coders. Classes and data types all have capitalized identifiers because they behave slightly differently than values and operators do. So what that means is this is not a type, it's a value. So we're going to call this small test size. And we're actually, just because I'm going to give that an underscore here. And actually, you know what? I could do this camel case as well. So G small. G. I could do this. Why not? Let's do it that way. G for global, and then this problem just goes away. Now, declaring of the types, I could either coerce this into a type, and then this gets automatically deduced as a type. Or I could be extremely explicit and actually give this its own type. Let's do that. Do I want to do that? I want to engage this solution from the point of view of I really like type safety. Programming languages that don't do really good type safety drive me nuts. I can totally code in them. I totally get why you would want to have the ability to just throw together code that works, work at it until it's polished and as bulletproof as you can make it, and then you just don't worry about the types because you just stop caring, I guess. I don't know. I don't know what the mindset is because it's really hard for me to get into that mindset. I've used Python. I can code in it. I really don't like its lack of type safety, and I don't like a lot of programming languages' lack of type safety. A lot of scripting languages just ignore type. I like really strong typing. I want the compiler to bash me over the head when I do something stupid that's purely type-based. So that's where I'm coming from, and that's why I am probably going to be explicit about types in at least some cases. But here's the thing about Haskell. It's a little bit like C++'s shift over to using auto in a lot of cases. Not because the auto keyword in that and say C# gives you a fluffy type or an indistinct type. What it gives you is it tells the compiler to automatically deduce the type from the context in which it's being used, for which there are rules in any language. Haskell takes this to a fairly decent extreme. You can actually avoid using explicit types almost everywhere except in perhaps data declarations like this. and in a few cases where the types get ambiguous, in a huge number of cases, you just don't need to provide types, because it will simply work. Except that some cases the types it chooses when you do constants is not exactly what you want. So for constants, I'm going to say this. I'm going to make these ints because otherwise they default to fully integer, and integer is a big int type that can be as big as you like. It auto expands like a vector does in C++. It's an auto expanding integer. You can make numbers as big as you like, but as a consequence for that freedom, it's also not very fast, or at least it's not as fast as int, and optimizing that away is really, really tough. So I'm going to use int, and this uses a value which is more or less like a long on this particular 64-bit machine. I'd have to look up what the actual range is, because if I wanted an explicitly sized integer type, I would do what you have to do in C++, which is to go and find a specific... I'm going to get rid of that, by the way. Don't need to look at that. There are explicitly sized integer types for when you need that sort of thing. This does have a known type, and at least for our purposes, it's big enough to solve the problem. So I'm just going to keep it really simple and not go any further into that. Now this gives us our integer types. That's literally it for that. I'm going to quickly... I'm going to go into here and make my compilation faster. Actually, I don't even need to do that because I'm doing this all in the REPL anyway. Right. Here we go. We're just going to say reload, which just reloads it, and it reloaded, parsed it, and I can now run it, but it won't do anything. Yay. Huzzah. We did not screw that up. And I've only gotten as far as writing constants because I've been babbling. We are going to go into, we don't need that. We might need, no, not really, because we are going to just use lists, and because of the fact that all the lists are compile time polymorphic, like they're generic, and you don't have a complicated way to initialize them, we're not going to bother using tries, should we? Suppose we could for completeness. Why not, right? Why not? So I think we can go... I think we can use type as an alias in Haskell. It has been a while. So we're going to go type tries equals as a type. I think we can do this. I think that creates a type alias. Well, it certainly compiles. It's either type or new type. I can't remember which one of them creates just an alias for the type. There is a difference, which you can dig into at your leisure. I may go into it at some point. That's not the point here. Let's get on with this. We're going to convert this over as reasonably directly as we can. So we're going to go and create this guy. So this is right angle. And the way we do this is we do, let's just write it out actually without types, and I'm going to explain why it's perfectly okay. We're going to say is right try equals try, now it's not try, is it try dot a, no, it's I can do a couple of things here. I can do it the functional style, which looks like this. In order to get at the fields of a structure, the fields themselves, for access purposes, become functions. But we don't have an object style syntax, at least not without bringing in things like lenses and views and stuff, which is sort of an advanced Haskell thing, and I'm not very comfortable with them. So for this program, I'm not going to do that. I may review that for part 2 of this because it's becoming increasingly clear that I'm going to have a part 2. So is right try is equal to, now I could do this. So it would be basically, unfortunately, these are all going to become global functions, A, B, and C, which I do not like. I wish they had some scoping of of naming conventions, but what this is going to mean, I am going to do this because I want to use A, B, and C as variable names elsewhere. Really don't like that. That's the one thing about Haskell I don't like, is that the names of the variables inside data structures like that, when you choose to name them, become global functions that are accessors to that data type. I would prefer it to have been scoped. It's not. One of those things I don't like about the language. But you live and learn. I could make them not named. There might be other ways to hide them. But I'm not going to. Actually, if I had it off in a module, I could probably come up with better ways to do that. But so I could do this. I could do try that gets a single value, and then I could do exactly, so this basically replaces this, and I could do this expansion. What I'm actually going to do is this: A times A plus B times B equals C times C, where A equals try A try Now, I'm actually not going to keep this function, and the reason why is because we can compactify this better than this. This is a very silly way to do this. So what we're going to do is we're going to do a reload, and it says parse input on open brackets. Why? Oh, because I have this thing in here. I don't need this here anymore. Let's get rid of that. Incidentally, whatever happened to our... there we go. I don't know. Microsoft Visual, now it's renamed the window again, so I'm going to quickly pop you guys back over to here. Quick check on the other console window. You can see that the program did eventually finish. Now, I don't have any timing characteristics on this, but it finished. It succeeded in, at least, a livable amount of time. I probably will have to time that separately and give you that information in a separate video. But we have actually generated all the values, all the triples that are unique, all the way up to C, the hypotenuse, being 10,000. So we're happy about that. We're going to leave that alone now. Back to our work. Here we go. So we've got this isRight function, isRight angle, I guess, if I want to be. IsRight triangle? What the heck did I call it? IsRight angle. All right, well, we'll call it that anyway. A times A to B. Okay, so if we have, for example, let's reload that, and we go, we're going to let try equals try 3, 4, 5. No, I can't do it that way because this is not C++. So I could do 3, 4, 5 like that is 3, 4, 5 like that. And this is building try out of 3 parameters. I could use the named versions like I demonstrated above, but let's just use the cheap way because I know how to do that. I can output what that actually is, and you can see that there. So what I can ask is right angle try, and the result is true. Right? So that works perfectly fine. And so we can also do isRight triangle 5, 7, 45. Pretty sure that just randomly picking numbers, it's going to say false. And you can probably do the math to figure out that that's not the case. So we know that the function works. And I'm going to write a test harness in a moment because later on I'm obviously going to want the same test harness code in this that I did in the other one. So... but this is kind of, this is perfectly acceptable way to write this. The where clause enables you to establish sub-expressions, which can refer to each other if need be, as well as being available as values expressed up here. But instead of doing it this way, we're going to do it a bit more of a compact way. And what this uses is structural decomposition. We started to see a little bit of this in C++. You see a little bit of this in C#. And that's where you take a value that's coming in and you decompose it. And one way to do that is you could do something like try ABC, and I'm just going to give these unique names, equals try. And that kind of binding will essentially decompose the structure and place the parts of that into the individual values. And if I do a reload here, that should probably work just fine. Of course, it's ignoring that because I'm not doing anything with these values. But if I substituted these up here, it would work just fine. But I don't have to do it there. I can actually do that right here. So what we're going to do here is we're going to do try. I could do ABC like that. I could also do A equals try A. Actually, it's the other way around, I think. This is not assignment. This is a decompositional binding, I guess. Try B equals B. Try C equals C. Come on. Come on. There we go. Get rid of that. And now, because I've done that, I don't need any of that. So that is, except I need the closing brace. You need to use the brace syntax when you're doing when you're accessing fields like this. One of the times that is perfectly reasonable to use brace syntax when also using the space bracketing. So reloading that, it seems to have allowed that. Seems to have loaded incorrectly. Let's see if it actually works. So let try equals 5745. Is right triangle is false. We're going to go all the way back to try 345. Is right triangle try is true. So this is another way that you could write that, and it's perfectly legitimate, so that's the one we're going to use. So here's a little Haskell syntax for you. We're also going to need GCD of A and B next, so let's just temporarily copy that over here. We'll very quickly whip this out. We're going to have GCD right, so GCD of A and B is equal to and we could what I'm going to do is I'm going to do it like we would do it in C++. Now I don't have a ternary operator available to me, which made the GCD writing in C++ kind of convenient. What you would have to do is something like this: if if B is equal to 0, then sorry, I don't think I need the then A else GCD B A rem B. And I think there's also there's a pair of them. There's a quote rem and there's div mod as pairs of functions, two pairs of functions, and they do slightly different things, and you can go look them up. I'm just going to use rem. I think this should work for GCD. And yes, I am kind of eschewing the unit tests here because I kind of want to get this done. Maybe I'll do the unit test writing for these individual functions between videos, so I'm not spending a lot of time on them. So let's check this out. Let's reload. We have a parse error on an open brace on line 24. Oh, because I still have this code. Duh. Do I need to then? I have forgotten. It's been a while. Yes. So, one of the problems is there is already a built-in GCD, so I'm getting this error that there's a redefined version of GCD. So what I need to do is I need to basically, I could give this a unique name, or I could use the built-in GCD, but let's just, for the sake of completeness, we're going to call this one GCD prime. And a tick mark after an identifier in Haskell is a legal part of the identifier, because it's sort of a very mathy thing to use ticks to represent variations on a value. And so they incorporated that into Haskell. So you're going to see that in quite a few places. I use it in quite a few places. In C++, maybe use an underscore instead of the tick mark. You just can't lead with a tick mark like that. So let's reload, and it works fine. And so let's try this out. GCD, say 6 and 3 gives us 3. 6 and 4 gives us 2. 13 and 5 gives us 1. 45 and 9 gives us 9 because it's the GCD. 45 and 6 gives us 3 because 3 goes into 45 15 times, 3 goes into 6 twice, so it's a good GCD. So that works out okay. So that's great, but that's actually not really how I would probably write this in Haskell. Ifs and elses are perfectly legitimate constructs. You'll notice, by the way, that it's not if condition then do something. It's if condition then value that should be the result of the entire if expression. Because everything is an expression in Haskell. Everything's a value. Everything gets evaluated. So this entire thing produces a value. So that's why I don't have like anything like a return statement here. The entire expression returns its value. So the entire expression returns A if this is the case. Otherwise, the entire expression returns this if it's the case, and this is recursive. So fantastic, right? But you probably wouldn't write this with an if and else in Haskell. What you would probably do is this. When you write a function, you can actually list it out. There's a pile of different ways to do this. And I can talk about guards later, and there's a whole bunch of other interesting things you can do. But what instead I'm going to do is I'm going to use pattern matching, which is, I guess you could call it a close cousin of decomposition. And I'm going to do this. If I find a 0, so I'm going to have, okay, so I'm going to clone this a few times here. If I find a 0 in the B position, then the result is just A. And if I otherwise, because it'll do this one by one, testing one by one until it finds one that can succeed. Otherwise, it's going to use the one that more generically matches. So this is a little bit like C++ templates, where you have a specialization in one of the values. In this case, we're pattern matching on a 0 in this case. But if it isn't 0, then it's going to fail the pattern match, and it's going to not consider that. It's going to consider this one. And so this is simply going to be GCD B a rem B. The back quotes. The back quotes are to turn a 2-parameter function into an infix operator. And so that's all that means. I could have done this rem AB instead, but without the back quotes. That's all that does. And it basically means any function can be used as an operator. Any 2-parameter function, anyway. So how does this work? Oops. Hang on. I want to make sure we have a tick mark here, otherwise we're not calling the one that we think we are. So that works. So GCD 6.3. Oops. And you'll notice, actually, here's the problem. In every one of those cases, we've been calling the wrong GCD function. So that's a problem. We didn't actually test out our previous code. It did compile, but I'm not going to go back and test it. So let's do this properly on this version anyway. 6.3 gives us 3. 6.4 gives us 2. 45 and 9 gives us 9. 45 and 6 gives us 3. 13 and 5 gives us 1. So it works perfectly well. This is a more Haskell-y way to do this kind of thing. To do something that has a recursive definition like this. Perfect. Next. Has common factor. Oh, actually, one of the things we should note is that is this a check to see whether or not A is 0, and then to do something about it. And so here's the question. I've forgotten how to I have forgotten how to test this. So Haskell assert, because it's been a long time since I've done this. So we need, it is in fact a function, and we basically just assert false x. So sorry, assert test. We're going to do that. What we do is we basically go assert test for whatever test we want, and then the value that comes out of it if we if it succeeds. So what this is going to say is assert a is not equal to 0, which is actually done with that. Yes, I know, for all of those who absolutely insist it's bang equals for not equals, just suck it up. I'm not interested. So we're going to do this, and in principle we have to do a parentheses like this. So we're going to start here. Oops, we need the assert here too. Now the reason to do it this way when you want to do asserts is because the compiler, just like in C++, optimizes out the assert code and just produces the final value when you do it in release effectively. It'll only be performed. GHC ignores assertions when the optimization is turned on with the -O flag. So we are going to, on purpose, go into the package. Actually, I think it's in debug mode when it's run in the editor. So we're going to find that out in a minute. Let's actually find that out. Let's try to reload. And we do not actually have assert available to us because it's legitimately just a function. So this is in... I don't know where this is. Is this in control.assert? I do not recall. I may be mixing up my languages. No, it's not there. So what we're going to do is we're going to go onto a thing called Hackage, and we're just going to Google very straightforwardly Hackage assert, and it's control.exception.assert. So actually import control.exception, and we're going to say specifically only import the assert item. I think it should work, and it does. Huzzah! So if we do this again and say give 45.6, it just gives us the value. There's no big deal there, no drama. Here, let's see what happens when we give a 0 for this. We get an assert, and it tells us where. It doesn't give us the pretty message trick like we did in C++. We may be able to find a way around that, including maybe writing our own assert code or doing something clever. We're not going to go to all that trouble, but we are going to put asserts in just like we do in C++, because why not? So effectively, this enables us to do testing just like in C++. Now another trick, just to clean this up, is if you have a tail expression that like this, that is wrapped in parentheses because it's being submitted as a parameter to a previous function, like this is assert, 1 parameter, 2 parameters. We can actually simplify this for all such tail wrappings by doing that, and that's just effectively the equivalent. And you may not like seeing that, but you see it all sorts of places in Haskell code. So that's all that means. It means you can get rid of trailing braces, because a lot of Haskell is about composition of functions, and so you're going to see a lot of my use of the dot operator. You're going to see a lot of use of the $ order to reduce parentheses. Another possible way to do this is say this. So this is a function with, this is effectively a function of 2 parameters where 1 parameter has been provided. So there's 1 parameter left, and we can get that parameter from the output of another function. So we can use the function composition operator. This is basically where g of f is effectively equivalent to f dot, this. So g of f applied to x. So this function takes x and passes it into f, and then passes the result into g, just like it is here. So that's what the dot operator does. And another way to write this would be effectively this, because actually the same logic goes for unwrapping a list of parentheses on the left if it's the only thing that you're doing. So that is also equivalent, I believe. Let me just double check that, because we can do that in the interpreter. So f of x equals x plus 1, g of x equals 2 times x, f of g of g of f of x, g of f of 3 gives me 8, because that's basically adding 1 to 3 and then multiplying it by 2. And then let me just make sure I've got this right. G dot f of 3, and we do the composition of those, call 3 is 8. And then also do this. All three of those are equivalent. In any case, these are all ways that we could do this. In order to make this the same, we would have to do that. Is that better? I don't know, because effectively if we didn't do that, it would first bind all of these, and that would just give a value, and a value does not compose with a function. You need a function to compose with a function. So I would either have to wrap these in parentheses, or I would have to put the $sign operator there. And in fact, I'm going to go all the way back, because the version of this that I like the best for this particular function is effectively, I'm okay with that version. So this makes sure that this is evaluated as a partial function, this is evaluated as a partial function, and then this applies what remains on this side to this. So this evaluates to a function of one parameter, because it used to be two, but we provided one. It's called currying. And then we apply that as the final parameter, because this gets in the way. So whenever you're reading Haskell code, the act of having a space after a function name binds the next things that are space delimited as parameters. Spaces in this sense are a lot like the commas in function calls. So let's get on with this, because we are slowing down and I want to get on with this. We did GCD. Let's quickly do has common factor. Just going to quickly pop that over here. All right, here we go. Let's do this faster. Has common factor ABC is equal to, and this should be relatively simple, GCD A, GCD of A and B, and then we're going to want that piped into GCD, and just because I don't want to get clever with parentheses and $signs, I will just do exactly this. So this is effectively what we have. Right? And I could break it down into two independent variables like I did here, and arguably, I could clean that up. That should be our has common factor. We should also throw in the asserts. So I'm going to do that again. A is not equal to 0, and B is not equal to 0, and C is not equal to 0. Let's try that. All right, has common factor 2, 4, 8. Oh, except that's not actually what has common factor is it? And actually, this is a badly named function. It should say has common has common non-trivial factor because we don't care about ones. And so this is going to return a value as currently presented. What we actually want is to see whether that is not equal to 1, right? And you'll notice that having done that, has common factor suddenly returns nothing because I didn't do a reload. Come on. True, it has a common factor. We don't know what it is, but it has a common factor. And we know that it's 2 because of what we just did. Has common factor 2, 4, 7. False. So there's our test cases. Has common factor seems to work. Let's move on. So we're going to want to do PyList by nested loops. Okay, so here's where things get interesting. All of the functions we've written so far are basically just, here's an input, put it through some transformations and tests, and put out an output. Haskell doesn't do loops. It's a blanket statement, but it doesn't do loops in the for loop sense. The reason is because Haskell doesn't do mutation. Yes, I know, for all you Haskellites, of course there are exceptions to this, and blah, 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 blah. But the point is that Haskell basically embraces the idea that once you set a variable to a value, it doesn't change. You don't change it. And every bit of other code that ever looks at that variable can depend on that. It means writing your code a little bit differently. But if you'll notice, one of the things that happens in a for loop is we're actually mutating a variable. Can't do that in Haskell. At least not in sort of most traditional, quote, traditional Haskell code. So we have to find an alternate way to do this. And I'm just going to double check my stream just to make sure everything's going tickety-boo on the stream. More spam. Don't I love spam? And I'm guessing the 2 viewers that have popped up on my channel are in fact just the spam people that have arrived. I really should find a way to block this bozo. But I am not familiar enough with how Twitch works. And I'm not popular enough to work it out, so that's fine. So I want to do this, but I can't do it with for loops in this sense. How do you do loops when you can't do mutation? Well, there's a couple of ways. One, you use a function that does the loop work for you, but you don't explicitly write a loop. You could call that a cheat if you want, because you could say, well, that function then that's doing the work for you is just doing a for loop. But the fact of the matter is that if you can't see it, for all intents and purposes, it doesn't. You don't need to think about it existing. But that's still kind of a cheat statement, because the other way you would do it is through recursion, or through low-level support. In case somebody's written a super efficient version in very, very low-level code that does use loops, but you use recursion. And this is perfectly acceptable in Haskell because Haskell demands, under the right conditions, that at least the GC compiler does, that tail recursion gets eliminated, so that at the very last thing that you evaluate is another function, including itself, that it turns into a jumping call rather than a pushing a stack frame and like building up stack stuff as you call deeper into the functions. It simply never gets deeper. And so this is perfectly acceptable thing to do in recursion. So I'm going to write this loop out in terms of recursive operations that effectively do the same thing as these for loops, and we'll see what that looks like. Again, this is probably not how I would really do it in Haskell, but this is our very first sort of non-trivial function. And so let's just get on with it. I'm not going to copy this over, but I am going to copy sort of that over so that I get the naming roughly similar. So it's got to be, it's going to return tries. You'll notice, by the way, that we haven't actually provided any prototypes for any of the functions. We did provide type information for some constants so far, but that's it. We can't call it with a capital because this is just a function. So PyList by nested loops. So we need to be able to take in a single number. How did we do this? We're going to take in a single integer and return the collection. All right. So, and we called that single integer, I believe we called it n, right? So we're just going to label it n here. And what we're going to do is we are going to, now, I could do something clever by, say, counting backwards or whatever. I'm not going to. What I'm going to do is I'm going to create a number of inner functions which actually do the work. So what I'm going to do is pylist. We're going to start at 0. So our target is n. We're going to go up to n, and we're going to start at 0. And so what this does is where pylist ni equals, and then this is where we're actually going to do our loop. But we're also going to have two versions of this, just like we did for GCD above, where if we've hit, we'd like to be able to say something like this, but it's not going to properly pattern match on that. Well, it might, but I'm not going to do it in that style, even if it can. I've forgotten whether or not that's legal. There are some clever things that you can do in pattern matching that are non-trivial. But we need to kind of do something like this. We need to say that when n gets to I, then we're going to do a thing. Or sorry, when I gets to n, we're going to do a thing. Now we could do this. Let's see. We could do this. Maybe I should do this explicitly. All right, let's do this explicitly. If I is greater than n, so if we've gone past the value, then, and we're going to want to build up a list here of the relevant items. Doing this by explicit recursion is not a very Haskell-y way to do this. I should point out, but we're going to do it this way anyway, just to give a correspondence to the C version of the program, and then we're going to clean this up, and then maybe go and try to do the same thing in C++ to do it a more Haskell-y way. So n and 0, but we're also going to want an accumulator, and we're going to start out with the empty list. Actually, what are we going to do here? We want, sorry, n. Actually, we're going to put n at the end. We're going to say 0 and at the accumulator. How do I want to do this? Parameter ordering. I'm going to put the n on this end, and I'll tell you why in a minute. But what that means is, what we actually have is the accumulated list. We're going to have the value I, and then we're going to have, we could actually pass in n, but n is never going to change throughout all of this. So let's actually not pass it in, because we have access to it by act of the fact that outer variables are available in the inner scope. Why pass it in? Pointless. So like I could pass it in here, and then I just have an extra parameter to pylist all the time, but let's not do that. We can leave it out. So if I is greater than n, then, and the value result of this is simply the accumulator, whatever result we've gotten to so far, that's it. We're just done, right? The next thing that we're going to do, else, we're going to want to call pylist with some modification of the accumulator, which I'll get to in a minute. And also, we're going to want to pass in I plus 1. Yay. Okay, so that's what the recursion is going to look like. Now you'll notice if I do it in this form, the very last thing that gets evaluated is a function call. So this is recursive, and it's going to end up evaluating that. But because it's evaluating something in a tail position like this, just like tail recursion, elimination, and a lot of other languages that allow it, C++ as well in some cases, although it's not mandated, this will not build up stack frames no matter how big n gets if we're careful. So as long as we don't do anything that requires us to store this value here and do other work, as long as it's the very last thing that gets evaluated. Literally the value of the function is the value of a variation call on the function. So what we're going to do then is we need to bind act prime to something. So act prime is going to be this is basically counting on C, right? So this is actually, we want to turn this into C. This is C. Right. So this is going to get slightly messy, and this is why we don't do loops in Haskell. But let's see if we can make this work. We need to be able to then make C available to those inner loops, because basically what we don't have are these. What we have at the moment is only this outer loop, right? Only the outer loop that involves C. And so what we're going to do is we're going to say ACK equals, so let's call this PyList C, actually, is equal to PyList B right. I have to think about how I want to do this. I need to be able to get all of the results from the more inner loops to be values that get passed back. See, here's the thing. In this guy, not only do we have mutations of the variables here, but we have another mutation. We have this. I can't really do this in a trivial way in Haskell. I can construct a container in which I can add items, but in Haskell that doesn't take the container and mutate the container. It takes a container and a value and gives you back a new container, and that's actually pretty fast in a lot of cases. And I'm not going to go into why, but that effectively means that I would have to write the code in such a way as to thread back the new containers through layers and layers of these loops. I'm going to have to do something like that anyway. But I don't actually have a container in this kind of sense that has to push back. What I effectively have is a list. And that's actually good enough for our purposes. We need to be able to append or prepend elements to a list in order to be able to brain has stopped functioning. In order to be able to build up the complete list. So what we're going to do is what are we going to do here? ACK from B is equal to PyList B. I should have chosen a simpler example for this puzzle, but we're going to do this anyway. We're going to provide the empty list here again, because we're going to basically mimic the outer behavior. Totally not the way you should be doing this in Haskell at all. And we are going to start its counter at, actually not 0. All of our counters start at 1, if you recall, for our loops. So these are all 1s, actually. So we're going to get ACK B from PyList B and 1. We are then going to bind ACK to be whatever ACK currently is. Now we could append, this is list append, the list ACK onto ACK, or ACK B onto the end of ACK. The problem with this is ACK is going to get bigger and bigger and bigger as this goes. And doing an append like this means that whenever you do an append of two lists, your performance is going to be based on how many elements there are in the first list. Because you got to go all the way to the end of the list and then you tack on elements in order to build the new list. Because you don't mutate lists, you build new lists out of old lists. This is not really the way we want to do this. We want to do this by way of, if we reverse these, we know ACK is going to be increasing, but ACK B could be actually quite short. And so what we're going to do is we're going to do this. Now that means that these chunks of ACK B are going to be appended in reverse order to the growing big ACK, right? And so we're going to end up with this daisy chain of little tiny pieces being appended to a tail that's really long. But that's actually pretty efficient. And if we keep doing this all the way down, what we'll end up doing is assembling this thing in reverse order. And we're going to find that out in a minute, because I'm going to show you what this does without us doing any reversal mechanisms or whatever. So we need to then call PyList recursively with that growing list and C+1. But ACK pi list b doesn't exist. So we're going to do another where. I should have chosen 2 space indents instead of 4, but oh well, that's where we are. We got enough screen space wide, so there we go. Here we go. We are going to do exactly what we did here, and yes, I know this is incredibly long and tedious with all the if and else's, but that's just the way it goes. We're going to collapse this down as we find a better way to implement this in Haskell. This is going to be one of our first refinements. But like I said, I wanted a correspondence roughly with the C code, and to do that, we need these recursive operations. So pi list, where pi list b is equal to if b is greater than c. Is it allowed to be equal to c? Did we allow that? I want this code to be roughly corresponding. No, it can never be equal to c. So we say if it is greater than or equal to c, then we're just done. We basically have ACK. Else, we have ACK C ACK A equals pi list A, again with the empty list and 1. And then we're going to skip over the where clause that we're inevitably going to need for pi list A. And we're going to say this guy's ACK is equal to ACK A added to ACK. Again, that's going to be in reverse order. Actually, this needs a new parameter, so this is going to be another ACK. So this ACK is independent from that one, separate parameter list, so that's fine. Because scoping. And then we want to return pi list. Hang on, we are getting lost in a few things here. This needs to be recursive up to pi list C. This needs to be recursive to pi list B. ACK. Nope, what am I doing? B plus 1. And actually that's ACK B, right? Yeah. I should actually give these unique file names. But then I'm going to have a renaming problem for a different reason. So we're just going to keep going the way this is going. So, and then the final result here is pi list B ACK B plus 1. So this is the recursive version of pi list B. Now the problem is we don't have pi list A. So one more time into the breach. If you're thinking, where pi list A ACK A equals if A is greater than if A is greater than or equal to C, then ACK else this is where we actually do our real work. Wow, this is a horrible nested mess, but it is effectively basically just the equivalent of this kind of recursive loop, but with a lot of extra conditions. Now we're going to compactify this a fair bit. So it's going to be less disgusting to read, but else. At the end of this, we're going to want to call pi list A with ACK prime again and A plus 1. And then this is going to be, we need to have we want to basically take each one of the we want to take each one of A, B, C, and we have A, B, and C as individual values here now. So basically, we now have try is equal to, and we're going to construct a try where try A is equal to A, try B is equal to B, and try C is equal to C. Right. Having done that, we also want to say if. So we want to be able to add it to the, we want to be able to build up ACK based on two conditions. Is there a new element or is there no new element? So ACK is going to take on one of two values based on conditions that we apply. So if some conditions, then, and we'd like to say ACK prime is equal to something like this. ACK prime is equal to new ACK, like a new version of an updated version of ACK. In fact, we're going to want try tacked onto the front of, and that's what you do when you have a single element on the left and a list on the right instead of two lists. We're going to add try to the try to ACK, and then we want a big set. Now that looks a lot like assignment, right? So this isn't actually going to work. But I'm going to, this is what you might do in C++. And in this case, otherwise we just leave it as ACK, like no change. The problem is that the scope of ACK prime in this case is only within this then case, this then part of the if. This is not how you do this. And you don't do assignments like this inside of if thens in pure Haskell functions. What you really do, because the problem is as soon as this finishes evaluating, ACK prime is no longer available at this scope. What you need is ACK prime to be at this scope. So what we actually do is this. This is how you solve this problem. So there you go. That should produce a new ACK prime, which then gets passed into here, and that gets then shipped out. Now, I have no idea if any of this is going to compile. No idea at all, but let's try it. And it fails. And the reason it fails is there's a parse input at ACK B is equal to, or is bound to, pilot B bracket 1. Which is on line, please give me a line number 37, and I really hate the fact that they've done some of this stuff in red that annoys me, but 37, because partially color blind or color deficient anyway. Else, and I've done the same assignment up here, and that is not going to work. So, what have I done wrong here? Because I have done the same thing. I've done an assignment because I've been working in C++ and C# for too long. This is not how you do this. So, parse error on input assignment. So, let me think about this. I've got to make this work. Else, and I need a value but not an assignment. Else, so here's what I've done wrong. So else, I have to have the value that I want to evaluate. So else this, where, and this is where I do the binding. That's how you do that, I think. I have been very, very foolish. You can only do bindings in wheres and lets, but as part of an else clause, you don't do bindings, you just provide values. So a number of ways to do this are you can do where and a bunch of extra bindings, or you can do something like well, I'll show you a let clause at some point in the future. You'll find out when we get there. So I have totally done that wrong, but I've also, of course, done this wrong down here as well. So what we really want, always look at what your values are supposed to be as the first thing in your else line, unless you're doing let, but we'll do that later. So that's what that means. And you can clearly see that this is quite nice to read, because it's pi less b is equal to this value if the condition is true and this value if the condition is false. And you need this where to push that into there, because that's a binding. And in fact, the bindings, because variables never change, the order of the bindings does not matter. So I could rearrange these as I saw fit, but I'm going to leave these in the order that they're in. So the same thing applies here, that the else condition provides that the else condition should not be doing this kind of thing. This is a value where those modifications have been made. There we go. Nested wheres, lots of fun. I've done something wrong here. Parse error and input act prime on line 59. All right. Right, because that is supposed to line up with that. It's actually supposed to be inside the where, because it's looking like this assignment is at the same scope, as at the same level as this, which would put it in the else, which makes no sense, because else's have to have a value. That is the value of the bit that I've highlighted. This is not a, this is a binding. This isn't sort of an evaluation. So this actually has to go inside the where clause, which means it has to be effectively there. And I'm betting that there's another bug there, because that has to be in the where clause of the outer scope. So the way we look at this is, here's the value of the else. In order to support that, here are the bindings that give meaning to sub-expressions. And I'm feeling very foolish for not remembering how to do that. We are going to get there. We don't have this condition sorted out yet. So if conditions. So we're going to have if is right angle try and. Is that how I do an and in this? I think it's how I do an and in this. I no longer remember anything. Or has common factor ABC. And if it's a right angle try and not, how do I do a not? Still not operator. Is literally just not. For reasons. And not has common factor. Now the problem is some precedence here. One of the things I could do is this. The other, and actually, let's just test to see whether or not that compiles. Yes, it does. Look at that. Hey, look at that. I don't know if it runs, but it actually compiles. I could do that. Because of the $sign can remove the trailing and closing parentheses. I can also do that, because that means that this gets evaluated and it gets passed to the functions on the right hand side. I could also probably do not dot has common factor AB $C, and that just looks horrible. So let's not do that. In fact, I'm just going to leave the parentheses in, because I find that somewhat readable, and I think the precedence means that this actually all now works. So what we're going to do is we're going to let try equals try, and I'm just going to use the shorthand here, 3, 4, actually no, I don't need to do that. Actually, I could just literally call All right. Tries. I actually don't need the let. I think I can do just that because I can do a equals 5, right? And it just does a bind. It does an implicit let. That's one of the reasons why the REPL is ever so slightly different than strictly what is legal in the full compiled version. But we can do this. You can assume that this has an implicit let. Tries equals, and we're going to actually call this right here and right now. Pi list by nested loops, and we're going to just do this. Why is it not letting me? Oh, look at that. I have a problem in the, can I do wrapping? Is this a thing that is a problem in the terminal? Line wrapping selection, quick edit mode, insert mode, enable control key shortcuts, filter, key clipboard contents on paste. Interesting. I did not anticipate that. Wrap text on resize, that's fine. For whatever reason, the REPL that's immediately provided to me does not do text wrapping of the cursor stuff, and I don't know why. I might be able to do this if I pull up a standard console window instead. Can I Haskell, no, GHC, search here, GHCI. I'll have to figure this out for future streams as to how to get the text to wrap. Windows and Haskell's text interfaces have always been just a little bit on the edge of only semi-functional sometimes. That's really just basically because Microsoft keeps screwing around with really not providing standard Linux style text output and creating versions of libraries for text manipulation that look like the Linux ones, except don't behave the same. And so there's a lot of specialty code in there. It doesn't really surprise me. It doesn't work all that well with PowerShell, but GHC set prompt. All right, so let's try this. Set prompt. There we go. Yeah, that's far more sane. So, right. It still only gives me a line, but that should be enough for what I can do. And I can do multi-line input. But anyway. Yeah, try list equals pi list by nested loops 10. So it's done something. And in fact, here's your first lesson on lazy evaluation. I can actually show you something here. I'm gonna say I can use the :print sort of pseudo command that's in the REPL, and if I do print tries, what I actually get is not the value. What I actually get is a thunk. Everything in Haskell is lazy. Absolutely everything, unless you tell it not to be. Not quite true. The lower level primitives aren't, unbox types, but everything is implicitly wrapped up in an evaluation thunk. So that's what my value looks like. It hasn't even been evaluated yet. And so the variable is storing a future computation, but if I ask for it, it will be forced. So let's take a look. Check that action out. Our code has output results, but it appears to be that A is allowed to get too big. So we've got a pair that don't work, but let's try that out. Let's fix this. Let's figure out where that went wrong. There it is. If A is greater than or equal to B, then we just return the result. So let's just do that again. We're going to do tries equals that. And in fact, let's just bypass all of this. We don't need the tries thing. Let's just evaluate it directly. 3, 4, 5. That's great, right? So let's do 40 because that's the number of them that we had from before. And what we get is everything out of order. In fact, it's in exactly the reverse order. And the reason for this is at the very innermost loop, we're adding all of the elements in reverse order because we're doing a prepend and not an append. Then each of those is grouped in chunks at the next loop out, where we're doing the iteration of B's, and those chunks are being added in reverse order. That's fine. So we're prepending the later reversed values to the earlier reversed values, and that creates a list that is reversed at the outer level. And that daisy chains all the way out. So what we end up having at the very end is a list that is in total reversed. So there's a couple of things we can do here. There are ways to rewrite this so that effectively everything gets added to the tail end without causing performance problems, but that requires a lot more of a rethink. But what we can do here instead is simply go up here and say at the very, very last moment when we're returning the very, very last value, let's just reverse it. Right? And that's just a linear operation. We're already producing a linear collection. The reason you might not want to do this kind of trick is because then that means that it has to evaluate the whole list in order to reverse it before it can ever give it back to you. So the tricks that enable us to do this completely lazily involve having to append to a list as we go without doing mutation, which takes a little bit of trickery. It's not really trickery, it's just a different way of thinking. But if we do that and we do a reload, there's our test case. Now, it's just outputting it as what Python would be considered the repr version, the representation version of the data. It's how you would rebuild this thing. You could literally take this and paste this value back in and it would give you the value again. And that's for lists and recursive or flat structures, pretty much of any kind, that don't have looping structures in them, which are hard to do in Haskell anyway. This almost always works, just using the show mechanism. Now, first of all, I want to print out those tries not as try A equals this, try B equals that, and whatever. This is very dense. I want to change that so the printed show version is just the triple in parentheses like in the C++. So I got to do that in a moment. The other thing that I want to do is I still want to write the code that does the because none of this happens when you run main. I've already effectively done this guy. It is now done. Yay me. And to do that, I had to make sure that the loops were done without explicitly mutating things. I literally just go in the next loop. I was literally calling a separate function with a new C. The old C and all the other stuff was left behind, but not on the stack. It was destroyed because it wasn't needed. So the optimization by the compiler did the tail recursion to eliminate stack frames. And the fact that I was giving the next function call a new version of C is how we do this kind of explicit looping, which we shouldn't have to do, and we won't. We will clean that up. Nobody should have to write that code that you just saw unless you're absolutely desperate. Huzzah! Oh, yay! Another viewer. Hey, hi. Come say hi in the chat if you like, or don't, whatever you're comfortable with. So, we have gotten to the point where we have converted this over to sort of naive, imperative-like Haskell that happens to use recursion for loops. And instead of mutating a collection, we're basically building little versions of the collections all the way up and then merging them back as we go. But we're making sure that we do it in a way that basically guarantees, not guarantees, but it makes sure that we try to merge, when we do merging of the collections, we merge in terms of the lists, we merge the short ones in as a prefix to the big ones, and so that we don't end up with buildups of having to walk entire lists all the time. We have to walk very few of the lists in order to do the append. The only thing that we don't like is that reverse at the end, but for our purposes, it doesn't actually change the big O notation on the operation. So for the moment, we're okay with this. Let's do the analyze tries. So that is going to go here. Analyze tries. So this is going to take tries. And what we're going to do is, we are going to have, it's basically a bunch of different test cases to see whether or not first of all, let's test to see whether it's true. So we are going to say if the list of tries that we are given, we're going to do this. If it's empty, then we say true. We're just done. So that means that in this version of the function, because it'll evaluate the first one, if it fails to pattern match, it's going to go to the second one. We know there's at least one element in there, so that helps us. So we're going to say first, we're going to do this basically, again, using where clauses. So we're basically going to say, first of all, is it ordered right angles is what we're basically going to say, because we're going to test both of them at once. Actually, maybe we shouldn't. Maybe we should, instead of being absolutely explicitly the same as the C++, let's do something like this. This is equal to are all right angles, and are all internally, I guess I'm going to call it internally ordered. That's where A is less than B and B is less than C, or A is less than or equal to B. Anyway, so are all right angles and are all internally ordered, and are pairs and are tries ordered. All right, so those are the three things that we're effectively testing inside that C code. So there we're going to do where, and then we're going to actually have to define or bind what these actually mean. So we're going to have this and this and this all have to be defined. So all are all right angles. So I am not going to do this by explicit loops. I'm going to give you a taste on what you would do to avoid doing what we did up in that other big ugly function, because that one we're going to actually clean up on a second pass. So what we're going to do here is we're going to say, are they all right angles? Well, we're going to do this by saying use the AND operation. And what AND does, and I'm going to show you this here, AND takes a list of booleans and returns the logical AND of the list. And if we have a false in there, it returns false. So we're going to do that this way. And we're going to feed into that. What we're going to do is we're going to test each and every one of the triangles. So what we're going to do is we're going to do a map. And map takes a collection, a list in this case, a list of some type A, and turn it into a list of some type B by way of a function that does the test. So we're going to say map. We're going to have a function here as a lambda in a minute, or something, and then we're just going to give it tries. That's literally it. So inside this, we're going to need a function that effectively takes a try and tells us, does it have a right angle? Is it a right angle triangle? Well, we already have a function for that, so there we go. We're done. That's literally it. Now, a question that you should logically ask if you're not used to Haskell and you're not used to laziness is, isn't this going to turn all of the tries in the list into its booleans first and then do the logical AND? And so you're doing a lot of work if some early triangle in the list gives you a false. Are you not, you go true, false, true, 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 true for a million trues, and then all of a sudden you're doing a lot of work you don't need to. The answer to that is no. And the reason for that is because everything, including processing lists with functions, is by default lazy in Haskell. So that every time AND needs a new element in order to do its testing, it's going to ask this mapping operation to go to the next element that it's mapping as it's doing its mapping to give a new value. In C#, you'll see a lot of this kind of thing done whenever you do iterables, like enumerables, where you're doing, especially when you're doing stuff using a yield what do you call it? Lazy list production? It's like generators. You're basically using the yield operation in order to take a linear thing like mapping a bunch of values to other values and doing it incrementally, producing what is effectively a list. C# lists are a lot like Haskell lists in their laziness. It's just that Haskell goes one step further and everything is lazy, including individual values and so on and so forth. So in the list aspect, you could do something like this in LINQ very, very easily in C#. Because you could do in fact, there are built-in operations, I believe, to do this kind of AND operation and the map operation lazily, and at the end you get out a result, and you don't have to overcomplicate it with writing explicit loops that early return. Because you're never in a loop that you have to early return from. You're always early returning because you're always producing only the minimal amount of information for the next thing that your outer level evaluator needs. So this is as efficient as it gets from the point of view of just using lists. Are all internally ordered. Oops, yes, and. Now, this is a slight problem in that we are doing two separate passes of the list in order to do this. So if you do have to get to the end on both of these, you will be taking a path through the list twice. But let's solve that problem in a minute. Because it could be that actually that the compiler could do some very, very clever fusion on this, and it wouldn't really surprise me. So it's not is right angled, but we want something like is internally ordered. Now we don't actually have that, so we're going to invent it. We're going to say, basically we're going to take a try, and we are going to, I think this is the syntax. It's been a while since I've written a lambda in Haskell. How sad is that? Because they are very nearly ubiquitous. Haskell lambda syntax. There we go. This is why we Google everything. Lambda expressions. Yeah, it is an arrow. And in fact, I technically don't even need the brackets in this case, but I'm going to leave them in there anyway. So we're going to say we're going to need to basically say the same thing as we did. Here we broke apart the pieces of the triangle and we did a thing. So what happens if we instead we could do an is internally ordered in this style here? Probably should. Let's first actually take this bit and actually inject it right in here just to say that we can. So what we need to do here is a little bit of jiggery pokery. We actually do this. You can actually do decomposition inside a lambda. It's perfectly legitimate. And so we're just going to say no, we're doing the positive version of this. Before we did an early false, like we did false tests and did early returns, and we're not doing that in this case. We're saying and all of this is true. So what we want is that C is greater than B, and B is greater than or equal to A. And is that the test that the opposite of the test I had here? I said they all had to be one greater than or equal to, what was my actual condition here? A is less than B equal to B is less than or equal to C. So actually what I should do, if I'm honest with the spec that I had, because it won't actually change the result any, except for the 111 case. We don't really want 111 to show up. So what we're going to do is A is less than B, is less than or equal to B. These are allowed to be equal because it'll be filtered out naturally, but we're going to leave that as less than or equal to C. So we're going to have to update the various versions of this later on. But I'm going to leave it like this, and the reason for this is we want to make sure that C is always bigger than A and B, even if they're equal, just so that we don't end up with a 111 case, because then I don't have to test for the 111 case explicitly. I could test for the 111 case explicitly, but I'm not going to. Or I could start C at 2 for that matter. Instead, would be another way to process that. In fact. No, let's not. And in fact, the way I wrote the code, so I don't have to rewrite the code, is that we have this. It's never going to be the case that any of those can be equal. Because I don't think the sum of two equal squares can ever be equal to another square. The reason for that is that that would mean that a plus, this would be a squared plus a squared, which is 2a squared. So 2a squared equals c squared. And so that would mean that if you take the square root of c, the a squared can become an a, but the 2 becomes a root 2, and that's not an integer. So I think that proves that case. So this is allowable as a test that won't break Pythagoras, and that's the way I wrote the code. As you can see, I did allow it to be equal here. All right, actually, I did allow a equal to b there. Sorry, just double checking to see what I've added and what I've changed. All right, this is what I'll go with. That's what I wrote in the code. I'm changing a spec to match the code. Yes, I know. I promise it doesn't change the nature of the program. And it doesn't change the output. So I'm going to live with that decision, and I'm going to implement it the same way here. So what that means is C has to be bigger than B, but B is allowed to be equal to A. And if those conditions hold, then this is an acceptable solution. And are all the tries ordered? Let's temporarily, you know what, give this true just so that I can see if this compiles. So let's just start with that. So yes, the 3 modules loaded. So let's do tries equals PyList by nested loops 40. And I'm going to say analyze tries. It is true. Perfect. I should actually test to see whether or not this works even when something's out of order or there's something broken. So what I'm going to do is I'm going to do this. Tries is equal to this, and we're going to append. This is going to be a perfect test. I should test all possible ways that this could break. But we're going to do try, and we're going to add one that is technically after but is misordered. So we're going to have a 40. Need a big one. We're going to have one that is valid but misordered. So here's what we're going to do. Tries is equal to the all but the last of them. All but the last of this list. So we're going to see, how many did we have here? 1, 2. Okay, so we're going to do this. We're going to do, how do I take the first n of an item? I can do, probably the simplest way is take, so, okay, there's our basic one. Tries prime is equal to take length of tries minus 1 of tries, and then we're going to do tries double tick, totally legal, is equal to tries prime, and we're going to add on a single item to the tail end, which is the same as the one that we did have, so it passes the right angles test, but we're going to do 35 tries, 35, 12, 37. So the last one is 12, 35, 37. We're going to reorder the last one. Try 35, 37. There we go. So tries looks like this. So that last one is misordered. So we can do analyze, tries, double tick. False. Okay. We're going to set up tries is equal to tries plus, and this time we're going to give something that is not. It is in the canonically correct order. I really haven't done an exhaustive test case. I realize that it's in the correct order, but it's not a perfect, or it is not a right angle triangle. So we do that, and then we do analyze tries. It says false. And we could do one at the beginning. I'm not going to bother, but I do want to do one that's out of order. So what I'm going to do here is I'm going to do one that is technically legal, but the one that's at the end, try 35. So the correct one was 12, 35, 37, right? 12, 35, 37. And I could do it that way. I could do it just as a prepend of an element too, but I'm going to do it this way. So tries looks like this. Same elements, but same tries, but the one of the ones that was added out of order. So if we do analyze tries, oh, it returns true. Now why is that? Because tries are ordered, has not been written yet. All right, how are we going to do this? Beforehand, we did an explicit loop where we had I and j as mutating iterators. And we could do that in a very similar fashion here. Instead of having mutating iterators, we basically walk down the list at 2 different points in the list. And we just follow the links separately, which is kind of what the iterators in C++ would do on a list type. I could have written it that way. But I don't want to do explicit loops. Kind of tired of explicit loops. Kind of tired of big recursive, like, doing recursion manually is actually not actually that bad like this when you've only got one level, and we probably would only need one level in order to do it properly, but I don't even want to do that. So here's what we're going to do. We are going to take the tries list and we are going to zip it with a version of itself that got its head missing. All right, now keep in mind we already know there's at least one element, so that means that tail tris is always defined. Tail tris is tris, but without the first element of the list. So this only takes one step in order to evaluate. This gives us the j iterator effectively from the C++ code. This is going to effectively be our I iterator, and these two walking down the list are going to be zipped up into a tuple. Actually, we could do this as a zip with instead. So why don't we do that? If we did an ordinary zip, we would end up with effectively what amounts to a list of try 1 and try 2, on and on and on. So this would actually, okay, so it would be basically try 1, try 2, and because I'm a real coder, let's do 0-based indexing, so it would actually look like this. And this would go up to however many elements there were. It would actually create a new list that was a zip of tuples of the individual old lists. And it stops when any of the things that we're zipping runs out of elements. So we don't go off the end. It's already got its built-in check to make sure that either tries or tail tries doesn't run out. Now there could be some optimization here where there is definitely a way you could optimize this, because obviously it doesn't need to test tries to see whether it ends. We know by usage that it never will. Compiler probably won't catch that unless it's got a really clever transform or like an analysis of the structure of the code. So we can make that faster, but early optimization is a fool's game. This gives us a list of tuples, and actually given that, why don't I pretend that that's what I'm processing. I'm going to clean this up in a minute. So if we have that produces the zipped list. We're then going to feed that value as a parameter to and a function and that value. So the function we're going to test is pull out the try A and the try B. That's decomposition of the tuple, right? Because we could pull this out as a value tuple. If we did this, we could do that. That contains both values. It's a single value that is the tuple of the other two values. This is decomposing it early, right in the lambda binding, and then we do. We want to make sure that these tries are ordered correctly. This is going to be a big long function. that looks a little bit like where's the C++ version of this? Whoops, we're going to save that. The C++ version of this looks like this. Now, in the C++ version, I should factor this out into its own function, internally ordered. I didn't do it there. I'm not going to do it here because I'm crazy. So, are we going to do this in a lambda? No, we're not. What we're going to do is we're going to say, how are we going to do this in a lambda? We could. Actually, what we can do is kind of horrifying. We can do this. Try AA. So this is going to be basically this and this and this. Okay, so be very careful about the way that you block this stuff out, and there are rules about the blocking, and I'm not going to go into that because I'm going to muff it up if I try to describe it. So what we're going to do is let's try AAA, and let's try B. No, sorry, I've done this entirely wrong. That's not right. This has to be the name of the actual, in order to do this kind of binding, this has to be the name of the actual parameter. I'm going to call this, how do I want to do this? I'm going to call this try, I'm going to try this try 0. Try 0, nope, not there either. I'm being dumb. 0, B0, C0. A1, B1, C1. And here is where we put in our test code. So to do this, we want to make sure that, now we had to actually test to make sure none of them were 0 either, right? Yeah. So we actually have and our tries non-zero. But do I even have to test that? You know what? To be compatible with the C version, I will write that. However, let's get on with this. The R tries ordered is going to be compatibility with the C version. A is greater than B, and you know this is actually is greater than or equal to. It's allowed to be greater than or equal to B. That was a bug in the C++ version because that is part of the test that we just described. So I had a different test in two places. I will rerun this just by the way to verify that we are not making a mistake. But I'm gonna live up to my own spec where the spec isn't completely broken. So so we want to say this is valid if actually that's not the bit that we're doing. We're doing this bit. I still had to fix that though. So here we go. If I is equal to no, this is allowed to be. But then B has to be greater than or equal to C because this is the negative case. So it's greater than B or greater than C, then return false. You got to be very careful when you use negated logic not to get it completely screwed up. So the logic here is that in order to be valid, because we're doing the positive version of this, we have to say that that strictly speaking, A0 is less than or sorry, nope. I am doing this ordering of collection case, and we want to say that it is good if C0 is less than C1 or oh, this is gonna be a little bit gross, but okay. or C0 is equal to C1 and B0 is less than B1, or B0 is equal to B1 and A0 is less than or equal to A1, I believe is the way that should work. We're going to leave this off for the moment because I want to make sure that this runs. Let's just make sure that that makes sense with what we had here. We should actually be able to allow, so they're equal, then B has to be greater than, because it does have to be unique. So so either they're, sorry, ignore that. Each triangle has to be unique. If they're equal, then we test to see whether or not the B's are out of order. Right. So we're doing the negated logic here, which is basically we accept it if C0 is less than C1, or if they're equal and B0 is less than B1, or these are equal and A0 is less than now it's either less than A1 or they are equal. This last one is allowed to be equal. I don't have to daisy chain that any further, so I don't have additional conditions. So let's got a bracketing problem in here, I'm sure. Yes, I do. The function and is applied to two arguments. Right. Because we forgot the map. So we want to map that these two values. So we're taking the zip as I have a zipped bunch of tuples. For each one of those, we're decomposing it into two triangles. That gives the result of the map, because the map requires the predicate, or the mapping function and the triangles. And then we're and that's just going to turn into a bunch of booleans, and then the and is going to combine them together. But that is kind of terrible to look at, and I could do a sub-where clause to make that more easy to read. Let's find out what that looks like. But we did get that. So now, having done that, let's go all the way back to where every time you do a reload, unfortunately, all of your variables that you set out get erased. And so if you really want to do proper testing, you actually do it in your source code. So there's that. Now I want to do this case where we prefix an out-of-order element. Well, first of all, so yeah, we'll do that. So first of all, analyze tries on tries. Fine. But analyze tries on tries double prime, false. And the reason for that is because it fails that ordering operation. Now, this is kind of gross to look at. I'll totally agree. First of all, this should be a function, probably. Do we want it externally exposed? Possibly. We could do it, though, if we really wanted to. Something like this. Is try ordered? And then we basically... No, sorry, are tries ordered. We need a pair of them. Are two tries ordered? And then we could basically do this code and pull that bit out. So maybe I'll do that. Equals, so just a little bit of cleanup before we get any deeper into this. So this is going to be this guy and then this guy. Equals, And then we have basically this, which then makes this a lot easier to read, because then basically what we have is this. And we can even just collapse this up here because that's not terrible. Does that work? Nope, got a bracketing error, but that's fine. I don't have a proper editor that basically I'm just using this in pure text mode. Realistically, I should have a Haskell aware editor, of which there are several. I just wanted to do this in the same editor as I did the C++ version, and I'm kind of used to having terrible editors, so I should probably fix that if I'm going to continue doing this. Couldn't match. Oh, right. Sorry. That's why that needs to go there, and then that needs to go there. Then, no, I failed this again. Zip tries, tail tries. So couldn't match try with try. R2 tries ordered. This is actually a tuple and not individual elements. So we have to decompose the tuple as well. That's fine. And there we go. So one more quick test just to make sure this isn't completely broken. So analyze tries is true. Analyze tries with the double tick is false. That's a little bit cleaner, and this is where I'm going to leave that function, except that we also had the R tries non-zero. So this is going to be sort of a version of this, where except we can just do them individually, so you don't even need that. We're going to do basically A is not equal to 0 and B is not equal to 0 and C is not equal to 0. Reload. Oops. Now, I have bailed right out of the interpreter. Because reasons. Conflicting definitions for R. No, R tries not zero. That's what I want. Reload. Variable R not in scope. That's an interactive. Oh, because why? Because I am not entirely sure why this is failing me. Stack GXCI. No idea why it's doing that to me. Set prompt. There we go. Unknown command. I don't know why this is doing this to me. Prompt. How do I set the prompt again? Jeez. No, it should be set prompt. Something really weird is going on in the PowerShell, so I'm going to close the PowerShell entirely. I am going to then bring the PowerShell back up. Tools, command line, PowerShell. No idea what was going on there. I got the editor in a really weird state and I just don't care. So set prompt. There we go. Jeez. All right. Did it actually maintain any of my stuff from way before? No, it did not. So tries equals pi. See, you can do tab completion. Gotta love it. 40. Tries tac equals take length tries minus 1 tries. I'm sure there's a better way to do that. I just can't remember what the function is off the top of my head. Well, no, I want the single tick for that. All right. Tries tick equals well, let's actually test these out first. So analyze tries, and then we could test a number of the other conditions, but what we're going to do is we're going to then say tries tick equals tries double tick. And this is going to tell us we're going to do we want to test the zeros case. So we're going to do 0, 1, 2, which is in the correct, actually 0, 1, 1, which is actually correct on all of the other counts, including, oh, maybe we should do 0, 2, 4. So that is correct on every count, I think, except for that non-zeros case. Our try is ordered. It's going to be ordered. It's going to be internally ordered, and it's going to be right angles, but it's not going to be non-zero. And that was a fail because this should be try 0, 2, 4 because I don't know how to type. Right. So analyze tries tick. False. Perfect. So that is our analyze tries functions completed. Whew. Right. Dump example tries. This is actually going to be fairly easy, I hope. So, gotta be lowercase. Dump example tries. So, we are going to do this. Again, we're not going to do explicit loops. You'll notice, by the way, no explicit loops in any of this. We used functions that internally you could think of as doing explicit loops, regardless of how they're implemented, but we didn't have to do it. We also didn't have to use recursion. In fact, by and large, if you're doing manual recursion, you're either doing something super exotic, probably, or you haven't found a way to associate it with standard collections and manipulation operations that Haskell already has. That is a broad statement, and somebody will take me to task for it, I am sure. So, let's go to dump example tries. We are going to do literally the same thing as before, except instead of mapping, so this is actually something, here's the thing. This is an I/O operation. Effectively, it is the same as this. So I'm going to demonstrate that, I haven't been doing signatures because I don't need them, because Haskell deduces those types just as concretely as they do, just as concretely as it does variables. But I'm going to do it here. It is effectively an I/O returning nothing. Well, except it takes a parameter, so it's not actually this. What it actually is it needs to take a parameter which is the list of. It takes the tries list, right? It's one of these. And then, as a result, it returns basically a null. For all intents and purposes, this is an empty object, you could think of it. It doesn't have any value except itself. You can't create different versions of them or anything. The I/O is represented as a tag that basically says, for all intents and purposes, it's a way of staying in the type system itself these values are things that need to be ordered and need to be processed through some sort of elevated state, elevated mechanism. And it's Haskell's way of getting around the fact that you're not really allowed to do mutation, and you actually aren't even really allowed to do sequencing in the traditional sense. Although in order to evaluate a function, you have to eventually evaluate its individual parameters, unless in Haskell they're unused. There is an ordering by way of eventually evaluating a function. But by and large, I could actually reorder everything in this where clause, and it wouldn't make a single bit of difference. Because ordering doesn't matter in a pure function, because you don't rebind anything. There's no situation in which a value means something different in one part of your code than it does in another within a block. So those could be completely reordered. Doesn't matter. Even if they depend on each other in some sort of I need to bind X to something and bind Y to something based on X, I could still reorder them because it just works that out. But in the real world, you still have to do things that involve state. You still have to do stuff that involves this is the way things are now, and this is the way things are in the future, and anything that happens afterward depends on the ordering of things that happened before it. Haskell does that by literally encoding that in the type system. You don't see this in very nearly any other language. And I'm not going to go into what this mechanism is because there's just no point. But what this enables me to, is no point for this project, but what this means is I can effectively now do things that require, whoops, I didn't want to do that. Sorry about that. I accidentally triggered a playback of a lovely gaming review group. Well, it's not a gaming review, but gaming play group, and they love doing Nova Drift, and I love Nova Drift. So there you go. Go play Nova Drift. Great little bullet spam game. Really, really polished. Absolutely adore it. Anyway, so let's do this. This enables me to now effectively have operations that require sequencing. And none of the rest of my code has this because I don't want it to. I want the rest of them to be pure values. Everything else that you saw before is pure values. It's a generation of a value. A list is just a value that contains internally other values in a sequence, and they're not even really sequenced because you don't really need to evaluate the individual values in any particular order as such. They have an order, but individually they don't need to be evaluated. So that's a long-winded way of saying I can now do things that require state, and communications with the outside world requires state. And it requires state that's buried off in this I/O universe. You can think of this as the world, and printing is one of those things. So what we have to do is we have to do things that involve, we can do pure values in here, and we will have to in a second. So I got to figure out how I want to do this. So effectively what I want to do is I'm going to try doing this more or less as we see here. So we're going to do max, can't do it that way, G max segment equals 3. So this needs to be in a let binding because that's how you do bindings of names while inside effectively an I/O block. So that's a value that we're going to capture. And now we're going to say this is going to take a parameter, so tries. So let gmax segment equals 3. So tries, we need to say the result of this is going to be so put string without the line at the end. We're going to say what did I do with this? I think I just had an open parenthesis, right? Yes. No, I actually had tries bracket for the whole thing. All right, so that's fine. Let's do that. And in the tail end, we're going to have the close bracket, the comment about tries, And between them, we need to do, now we still can't do loops. There's still no loops in here, even though we're in the middle of this IO block. We have to do that through recursion or through things that do recursion for us. So, what we are going to do is we are going to effectively do another let, and I may get rid of this let in a bit, but we're going to do this just output one per line. We didn't have it comma separated or anything. It was just one per line, so it's not really a very helpful print in the ability to paste that back into the code. But we're going to do it the same way as we did in C++. So the try lines is equal to, and we're going to map. There's probably a better way to do this, but I'm going to try it this way. So for each of the tries, we're going to take a try, and we're going to turn it into what happens when we get do show try. So actually what we could do is we can collapse this down into map show. So this turns a list of tries into a list of the thing that show does to each try, which is to turn into a string. It's a list of strings. So try puts is going to be equal to map of put stir line. And actually these are all put stir lines too, I forgot. This is going to be on a line of its own. So line. Put stir line on try lines. Now I could combine these two things, and I probably will in a minute. But first of all, this turns it into a list of lines, and then this turns it into a list of I/O operations. Now, because this is effectively lazy, try puts. This is a pure value. It just a pure value that is a list, and in the list, each element is an unperformed. It's a value which represents an unperformed action. So this is still pure so far. What we then need to do is take this list of I/O actions and perform each one of them as an I/O as a universal I/O action. And I believe that's sequence. So T sequence. T, by the way, is what you do to get type information on something. Sequence takes a traversable, which is fine, a list qualifies, and a monad, which is effectively what I/O is, and I won't go into what that is. And it says that and so that's for M, for type M. Sorry, it takes a traversable of actions on an item and turns it into an action on a single action on a list of items. And so it's basically a way to sequence a pure list of impure actions. So hopefully we can do this. So this is how we effectively do the loop over the tries in order to perform individual operations, or one of the ways that we can do that. There's so many ways to do this stuff in Haskell, it boggles my mind, but let's just start with something that we know, and we'll go into the weird stuff later. So let's try reloading. That's frightening. It compiled first time. Either genius or great explosion coming. Isn't that the meme with Fry? I love that one. From Futurama. Massive explosion coming. So dump example tries basically takes a list. Except that that's going to dump out all of them, and so that's not an exact example of our program. But let's make sure this works for the short version of tries. So we go back and say tries equals this. That gives us a short enough list that it doesn't matter that it dumps all of them. So dump example tries. Check that action out. Now it's not in the format we want because the show operation for tries is fully explicit like this. So maybe I want to do something different. And what I might do is just maybe go, pretty show, and then write that out in a minute. But what I want to do is get this operating on longer lists as if it were like with the possibility of breaking it into two pieces. So Okay, so what we want to do is say, so that's all of the lines. So what we're going to do, though, is we're going to create a we're going to say that's all the lines. We are then going to, how do we want to break this up? We want to make sure that try lines, try puts does something slightly custom based on how big try lines is. So what we want to do is I want to see whether or not the length of the list is at least 7 items. Or at least, sorry, double Gmax. If it's 6 items, we're fine. We just do the normal thing. So we're going to do something like, and we're going to do this, instead of doing an if, we're going to do what's called a guard, because this is going to show you what I'm going to do to the code up above. So what we're going to do is we're going to put what's called a guard in here, and this is a test. It's another way of doing sort of like the pattern matching thing, only the conditions can be more elaborate. So if tries has, I'm gonna put an explicit Boolean in here. I could put any expression I like, but has at least is small list for our definition. Then the result is just to do the mapping. Otherwise, let's go and line this up because why not? Otherwise, we're going to do something a little bit more elaborate, and I'm actually going to put an undefined in here because now what that does is, because everything's lazily evaluated, it'll never evaluate that. And if it ever does evaluate that, because we get into that code, it'll literally abort the program. So this is a way of doing a kind of an assert at the value level. And there's a bunch of technical reasons or a bunch of technical descriptions on what this actually means, but that's what it means in a practical sense. And it's a good way to stub something out when you're sure you're not going to use it right away. But what we need to do is we need to define is small list. And we could do it in a number of places. We could put a where clause in here that applies to all the guards. But instead what I'm going to do is we're going to have, say, is small list for some list is equal to, and now we need to define this. So we need to say if now we want to the only way to find out how long a list is to walk down the whole thing. I don't really want to walk down the whole thing. I could probably say something like if length of ls, so let's this is going to pass into parameters, small list try lines. So why not write this in a universal way, because I just feel like it. If the length of ls is greater than g max segment times 2. So I believe how the other code is written. It says if it's less than or equal to, then do the short version. Okay, less than or equal to, let's do the short version, is small list. The problem with this is this has to walk down the whole list. But you know what? This is just part of debug, and I can tell you how I would solve that in a minute, but let's just get this working. Otherwise, so in this otherwise case, what we're going to do is we're going to say, we're going to map, put Sterling on take Gmax segment. Really wish it was a little bit more aware. Take max segment try lines. We're then going to attack on a thing, and then we're going to attack on another piece, which is the same thing, which is 2. We're going to have to walk down at least. We're not going to make this super efficient. I'm not going to worry about making this super efficient because it's just an example anyway, and this is never going to be timed. So what we're going to do is we're going to drop length of try lines minus Gmax segment. So we're going to preserve all but the last Gmax segment of them. And then in the middle, we're going to put Sterling ... So this is still using the same sequence operation, it's just that we're building the sequence differently. The other way to do this possibly would have been to, I don't know, there's lots of different ways to do this. This is just the way I chose to do it here. I didn't get this one right, but there's possibly an indentation issue here. So let's figure out where I screwed up. Because I have too many of these. So there we go. Different problem. Can't match string with int. So length of try lines minus G match segment. Because the things we're assembling here are the strings. Because then we're mapping put Sterling to each one of them. So I didn't want to do a put Sterling on something that had an element that was a put Sterling. That makes no sense. So we're still hosed. Length try lines minus Gmax segment. All right. How do we figure that? What am I doing wrong here? So try lines is a list. Length try line should give me a number. That should be a number minus a number. We're then dropping should be that. But then I want this to be wrapped the same way the other one is. So let's try that. I think I just got the... Oh, we got a different thing here. We got... Couldn't match char with IO, etc. Okay. So the problem is that it's doing map of this and then try to do the append because it's an order of operations. Now, rather than wrap this entire thing in parentheses, I could wrap all of this in parentheses, but instead I'm going to use the trick with the $sign, which basically says evaluate this and then use that as the parameter to the last to the tail end of this thing. So let's try that. There we go. So let us get tries. I'm going to do dump tries. Still works the same way on the small version of this. And you can see we're actually doing in the REPL what we're going to eventually be doing in main, and we've been doing it all along, which is a great way. I love REPLs, and I should actually start to use the REPL more in Visual Studio. It's not quite as powerful as this, though, at least not in my opinion yet. But in any case, let's go to 1,000. That's going to take a while. In fact, for the moment, it's going to take too long. So, oh crap, I actually bailed all the way out. Am I now going to have to reload the... Yeah, okay, so now we're going to... Yeah, Control-C does bail out of the entire thing. More's the pity. I wish it didn't do that. There's no... I have to figure out if there's a way to halt it without breaking out of everything. But in any case, it doesn't matter here, so... Instead of doing 1,000, let's just do 100. And there it is. Now that's quite a bit slower than the C++ version. And that's fine because I'm actually literally doing it in the REPL. And the REPL doesn't fully compile the code that it slurps in as part of the project. It'll use compiled stuff that you've already got precompiled. But it's actually doing an interpreting, as far as I know anyway, of the actual primary file that I've got here. So we can see that this is in fact now fully working, except that it doesn't quite look like the C++ version of this. So we are going to map simple tuple show for tries. And so what we're going to do is we're going to come up here. It's not simple tuple show, it's simple try show. So, and this takes one of these decomposed. And this is just going to, we are now going to, now this is a pure function. It produces a string. It doesn't actually do printing. So what we want is we basically want to do the value that we're going to produce is, that was kind of clever editing by the editor. I kind of see how that would come about, but in any case, that appended to, I do another append there, and in the middle we have show A appended to show B appended to show C, and I'm going to need some commas in here. So that's now this the append operator is right associative, so this does build this back to front, but then that ends up being the correct value. So this is pretty efficient when it's with an explicit list like this and you're not iterating in a loop and appending to the wrong end. So that is literally it, I think. So except I need to go to take simple try show and just dump this in here. And so this now gives us, there we go. That looks like, and let's just run it again with a smaller, we're going to go back to debug mode. Debug, please. Thank you. We're going to go back to the number of elements being, the big elements being, let's say, 1,000 or 100. Let's say 100 to match with the one that we just did. So, looking at these two outputs, let's make sure that they're pretty close to the same. Tries 3, 4, 5, 5, 12, 13, 8, 15, 17. The dots come in. And then we got 13, 84, 85, 39, 80, 89, 65, 72, 97, close brackets. The output is, very, if not identical, then very close. I think it's identical. We now have two programs that effectively solve the problem. And I guess except that it doesn't do it through main yet, so we do have to do that properly. And so the very last thing that we have to do is to write the bit in primary tests where we do these three things. So let's see what we're going to do here. This is the last bit, because after this I'm going to compile both of them, and I'm going to show that the Haskell version is probably not quite as performant because we're doing this in a very non-Haskell-y way, but it should still do quite a bit better than running in the interpreter. And then we will start to optimize the Haskell side, not just for optimization, because that's not really the point, but also to clean it up, to do it a more Haskell-y way, because you can always get the Haskell super ugly to the point, or very nearly always, to get to the point where it's getting C-like performance. But by that time, you've made the code really, really disgustingly imperative. And yeah, let's see if we can avoid that. Optimization is the point, but cleanup could still give us some good performance benefits by making it more Haskell-y. So let's see what we have to do here. We want to do, let's see if we can copy these out bit by bit. Actually, let's just take this whole thing. So what we've got here is the primary tests are, now instead of do something, what I'm going to do to give this some scoping is I'm going to make this explicitly a lambda that takes in something that we're going to ignore. That's what we can do as the underscore. And then we're going to give it, we are going to give it effectively, think we can do this, and then we want to apply that to a null operation. Actually, we shouldn't need that, because if we do that, and we produce something that that results in that final null operation, then it should stitch itself in. But I want an interior do. Can I even skip this and just do another do? Okay, so we're going to test this. It's been a while since I've had to do this, so let's try this out. Put Sterling inner scope. Oops, that's not the thing I want. I could type, hey, check that out. Okay, now we're going to start using main. So there's your inner scope. So I don't even have to do anything clever with lambdas and deal with how this stitches together in the do notation. I can just do an inner scope. And the reason for that is we are going to effectively do this. We're going to take all of this C++ code and we're just going to basically translate it sort of in line here. Here we go. I guess we can get rid of the brackets. So we're going to say, and we need an interior let, because these are going to be let bindings. So tries by nested loops is equal to pylist by nested loops, and we don't need the parentheses there or the semicolon. We're also going to bind tries by nested loop success to be analyzed tries based on this, and this becomes Lillet. Whew. Everybody still with me? All right. Tries by nested loop success equals analyze tries by nested loop. Okay. So, and then we have two output statements based on the consequences, and then we dump the example tries at the end. Now, actually, if it succeeds, we want dump example tries to occur at the end. So effectively, what we have to do here, what we want to do here is we need to have as the last line in the do block, we basically need to have something here that says that is a value that says what to do as sort of an action. So we can do an if at this level. We can say if, this is almost exactly what we want. If this, the result of the if, the expression, is in this case an action. So this is very much more like how C++ does things, or any imperative language. So put Sterling this thing, else put Sterling this thing. So what this tells us, by the way, effectively, is that Haskell does have sort of an imperative mode, if you like, by way of this I/O mechanism, this basic sequencing mechanism. A monad, won't go into what monads are right now, but for our purposes, it's a sequencing mechanism. But you don't write code in this manner all the time, or in fact, I don't, because I like writing in pure value evaluations. Can't get around that for I/O though, and in some cases, you just have to get down to sequencing something that involves state. And there's a couple of situations where you really can't avoid it, even when implementing an algorithm, or at least it's quite hard to do. But in most cases, you can do stuff fairly purely. I have found so far. Not that I've written, commercial level Haskell code, but anyway, we're going to continue on. So this looks a lot like standard C++ code. This is just, if condition, then do a thing. This is very imperative style. We are going to, though, actually do this. We are going to say assert on this, and if it succeeds, then we provide as the value of the else clause the action that we're going to do. So effectively, the result of this entire thing is still effectively the type of the result on the right-hand side. So from a type perspective, this works fine, and it will never get to the point of doing the failure if it asserts, which is actually, now that I think about it, not what we want to do. So what we're going to do here is we're just going to do this. We're going to do the put sterling, and then we are going to assert, and the value is just going to be false. Actually, no, it's going to be, we need to do nothing. I'm not entirely sure if there is a do nothing operation at the, how do I even do that? Because assert it has as a side effect its crashiness thing. We want a null IO action. So I'm going to actually look up what the canonical way to do that is. Haskell null IO operation. IO method that does nothing. Right, duh. For reasons that I can't believe I forgot this. For reasons that I won't go into, one way to get a value elevated up into that IO state universe is without having to have a sort of a function that does it, is to use return. It's a way to get a pure value. This here is a pure value. You basically elevate that up into the state, into the IO state universe, and use the return to do it. Now that is not a return statement like in C++. Do not confuse it for that. It does not suddenly end a function. What it does is it elevates a value up into the IO context. So basically that is itself a null operation. It doesn't do anything as a consequence of evaluating it as a sequence, in a sequence. But that enables this to work the same way my C++ does. Instead of having this as a part of, in substitute of this, because that would mean that this would never get printed, and I kind of want to mimic the C++ version of this. So, same thing goes here. Once more into the breach. I'm forgetting my thens. Let's add in a then. Then. All right. There are other ways I could do this, by the way. I could have said put sterling, and then as the parameter, I could have a pure value, which did the test, and then return a string. Doesn't matter. This is the way I'm going to do it. It's very, very C++-like. Else. Yay! And then we can do an assert. And actually, this has to be assert not that. Oh, no. We want to assert that it actually succeeded, but we know that it failed, and that's why it's going to explode. Again, not really the way you would normally use an assert, even in Haskell. I just do this again because it explodes and provides a message and provides a note on where in the code it died, but this enables a message to pop out to say where. So it tries by nested loop success, so that's that one. Hang on. No, I didn't need 2 copies of that. I don't know why I wrote that twice. I'm an idiot. How about if I'm an idiot? I'm apparently an idiot. Because I have a different version of it for the long example, so that's fine. So let's just make sure that works. Dump example tries, because it's lowercase d. So here we go. Couldn't match the type. This, incidentally, does not need that. Put sterling is applied to 4 arguments. So that's on line 114. I'm not sure why it thinks that. Because it thinks it's indented too far. Put sterling, no, that's not the reason. I got a tab in here I didn't expect. Come on, brain. Couldn't match type of... Okay, so in the same mode of do block, if tries by nested loop success, then because compound elses... elses with compound operations need a do to stitch them together. So a single value, this is a single IO action, it's fine. This is not a single IO action. This is, in order to have a chain of IO actions turned into a single IO action, you need a do. I could put a do up here, I suppose. Is that going to work for me? Yes, it is. But now I have small test size, except now it needs to be G small test size. So there's this. So there we go. Let's try that again. There we go. So now if we do main, ta-da! All right. Hey, we're getting close. We're getting really close to parity, at least in behavior, even though this is really crappy Haskell code. And not that great C++ code, to be honest. So we're going to want another copy of this do here, except in this case, we're going to do G large test size. Hopefully. Reload. Okay, it did not like that. Variable not in scope, large test size. Did I not put one in here? Oh, I call it big test size. What did I call it over here? Big test size. All right, it's not large test size, it's big test size. Who knew? Me. I'm just an idiot. All right. So this is how you would write this. All right, compile, hit main. It's really not going to like that, is it? It's not going to like that at all. How big did I make that? 10,000? Crappy death. All right, so we're going to start at 100. We may have to kill this. I'm in fact certain we're going to have to kill this. Oh, did it stay inside? No, it didn't. It bailed all the way out. That's unfortunate. Stat. Yeah. So this is going to be, we're just going to run main. Here we go. And scope M, because we've gotten into a weird state now where it's not actually getting all of my characters. I don't know why. All right. Don't know why that's happening. It might have to resort to using the original command line, developer command prompt. Except I haven't got that one set up for easy viewing. So, good to know. I will test that out in the future to see whether or not it's just because PowerShell it doesn't behave well in PowerShell. That's totally fine. In reality, one of the better ways to do this is to use this from within. I would expect within MinGW64 or whatever that does the sort of Unixy shell on top of Windows, and it gives a slightly better console window for stuff that is more Linuxy. But this doesn't do too badly, so let's just do it. Oh, this is in the wrong place. So. There we go, pulls in our values, and we're just going to run main. So that did up to 100. I could do 1,000 maybe, and it would just take a while. But check that out. So we have now done in main what should be being done in the C++ version. So let's run that one more time. Hopefully this is still all coming across in the stream. Oh, except it's the command window is a little bit off to one side because I moved it that way earlier. But that's okay. You should see enough of this to be able to see that the output result of the second one, the first one and the second one, I think, are in fact exactly the same. Check that action out. Okay, so now what we're going to do is, so we're going to quit the interpreter. And we're just going to go stack run, which should then compile it so that we can see what this looks like when all the optimizations are turned on, or at least the basic ones that are important. Now keep in mind, again, not really good Haskell canonical Haskell code for a lot of this. A little bit too much explicit recursion. We need to see that's a lot faster. We need to adapt this to make it more Haskell-y. And then we're going to take the C++ and see if we can make that a little bit more Haskell-y, or at least a little bit more in the functional style that operates as if things are data transforms rather than imperative operations. A style I quite like. So, final thing, this is going to be a terrible shootout, and this should not be an indication of everything Haskell is capable of. But yes, when you program a lot in lists, and when you start doing explicit recursion on those lists, the compiler has a lot of difficulty like fully optimizing that away, because it doesn't necessarily know what you're doing with lists. The minute you start using more canonical operations, it can do all sorts of crazy transforms because the transforms that even C++ generally can't do, because C++ allows mutations, so it can't look at a function and easily know what may or may not change. That's a bold claim. But in any case, we're going to see what happens when you take that up to 10,000 again, and we are going to risk setting this up to 10,000 again, except when we terminate this, it's not really going to matter. So let's get an idea. So now what we're going to do is we're actually going to quickly take a moment to fill out the timing part of this. So what we're going to do is we're going to take the large one, because there's no point in timing the small one. We are going to basically take all of this, and we are going to actually factor that out into void big test 0, I guess, big test. I don't know why I used underscore based function naming for these, but I did. So there we go. And this is going to be badoink, so that's fine. And big test 0 is going to get called by this, so we know that it works. And let's very, very quickly drop that down to 1,000, and we're going to say run this in release mode. We're going to and again, for whatever reason, and I apologize if I've accidentally goofed up not showing you the, oops, that's not what I want to do at all. I apologize if I have inadvertently shown you did I do 1,000? I only did 100, so I was showing you only hundreds on this. I'm gonna have to show you. I'm gonna have to double check that. This is Microsoft Visual Debug Console. No, that did show the right one. Okay, so there's the 1,000 element version on that side, done in this style. So, or done with the factored out big test function. So we are gonna go. We are going to go and say where is our testing? So this is the thing that we're going to factor out and call big test. big test 0 big test test 0 equals do equals paste. I think I can still, even though it doesn't know about, yes, I can still do the auto indenting. So that's my do for big test 0. So let's make sure that works. Okay, so what that tells me is I'm not going to go above 1,000 for the Haskell version of this. So clearly some optimization necessary in order to make this practical for the Haskell side of things. That's really unfortunate. I thought it was going to be a little bit faster than that, but that's okay. Did I make sure that that was set? Oh, that's why. Big test size is up at 10,000. All right, so let's restart that again. For heaven's sake. Okay, that was a thing. I mean, it's still going to be slower. Not because Haskell can't be made faster, like I said, but because this is not the Haskell-y sort of style of doing this. Oh, hell! That was actually pretty fast. All things considered. So let's just double check that the values are right. They all look right. That's fine. So the code works as appropriately. Let's get some actual timing in on this, though. Now, we already have the time it function in there. So what I should be able to do is say that in the timed tests, we're only going to do... come on. There we go. We're going to re-enable that. And then we're going to go big test 0, except what we're really going to do is auto VT equals time it. And then we have to pass it something that it will evaluate in the future, which means we can't give it a value directly because function evaluations are not lazy. But time it is undefined. Why? Because I have to go in and find that function, and I can't remember how it's called, so give me a minute. Okay, we're going to add an existing item, which is time.h, which should have been in there. It doesn't need to be in there to build, but so here's my time it header. We're going to ignore how this works exactly. We are going to do we don't want to actually time. So how do I want to do this? I don't actually want to okay, I'm going to think about this because I kind of want the value to come out, and I don't want to be timing the generation of the list to the console. I don't want to time that. So what I would like to do is actually use this version of it. And let's ignore the template wizardry that I wrote in here. What we're going to do is we're going to do time it, but we need to do a couple of things first. First of all, we're going to say that this is big test 0 I'm going to just call it IO in deference to the Haskell version of this. Because what I actually want to do is, let me see, how do I want to do this? All right. Right. or we can call this big test data. What is it used in templates? Value. Let's call it value. Maybe we can do that. Now you know what, we're gonna be in deference to the Haskell side of things because I like identifying, like in this case, the point here is that what's imperative and what's imperative and what's not. So we're just gonna do that. What we're gonna do in here is the actual evaluation, which is to do this, and this is going to be that's the value. We're then going to say we're not going to do the analysis because that's correctness based stuff. So what we're going to do is we're going to say this is going to be returning a tuple, which is going to be a time value, and the wonder if I could get away with this because C++ does C++20 allow statement list for I'm not using C++20. You can do certain kinds. I can't. Yeah, I had to return explicit type. Although what I could do actually is this auto return type deduction, so I don't have to figure out what this value is beforehand because I don't really care. So we're going to return. We're going to say auto t or dt is equal to time it this guy, and we're going to give it a value it has to evaluate. And so in order for this to work, we can't do this because it's going to evaluate it and not time it. So we're going to say we're going to give it a lambda to call that has in it this. So we're going to return badoink, but this is going to defer the execution of that until the function is actually called by time it. And as a side effect, it's also going to evaluate the time the time that it takes with just a elapsed time timer on either side of it. What that means though is that this is no longer needed. But what it also means is that we can use a C++ 17, I think, 14, I don't remember. We can actually do structural decomposition of tuples. And I guess other things, but specifically tuples, because that's going to return a tuple. And so what we can do is we can say dt is mapped to the first value of the tuple, try is mapped to the second. We don't care about the types. Figure it out for me. Yeah, there we go. That's how we do timing on this, and then we get a value out. We're then going to return actually, do we want what do I want to do here? I am going to change this. Big test 0. Yeah, I'm just going to call this correctness. I thought I could somehow fuse these two together, but I'm not actually doing the same operations in both, so it's not really. So the big test 0 timing. So I'm not actually going to return anything here. So having done this, I'm not going to worry about whether or not it's correct because I'm going to assume that's already been tested. I am going to dump out the example tries, but I'm also going to dump out okay, what is time? Which order does time it actually output its types? It outputs the time as the second element. So I've got these backwards, and that's totally fine. I wrote the function, I should know. All right. Elapsed time dt. Now, these are going to output probably two different formats of floating point, but I can't be bothered to format my floats. So we'll just have to adapt. But let's, so that's going to be correctness. So we got to fix this up. That's got to be that. But then timed tests is going to be big test 0 timing. And we don't have to do the time it bit of it because this is just basically, this is just a test case buried in code. So here we go. Built first time. Either genius or massive explosion coming. So let's run this and find out what happens. So the timing, elapsed time was 0.135 seconds. Let's do that, just run again, just to say that that's roughly consistent. So roughly consistent. We're going to do it on a bigger version of that. But now we have a structure that we can use to sort this out. So there's our primary test. There's big test 0. Correctness. This is terrible Haskell code. Slightly terrible C++ code. I've already said that. Okay. So we're going to do timing. Okay, so we don't need this. Don't care. We want to time that value. Now here's here's the thing. Everything's lazily evaluated in Haskell, so that even though this is a binding, this line itself doesn't actually do the evaluation. It just binds it to like a future computation. Effectively, everything's lazy. Everything's lazy. Almost everything's lazy. Somebody's going to catch me out on that. So what we do here, we can actually do let dt. Actually dt, so we're going to do something here. We're going to do vt, I guess it's vt, is equal to, we can actually decompose this. So we can say tries by nested loops. Okay, we're going to do this the same way as in C++ effectively, except it's a tuple and not a, so it's a tuple just like the other one is, except the decomposition looks a little bit more like a tuple. dt is equal to time it, and we just give it effectively. I could bracket that, but I'm going to use the $sign trick. So we don't need this anymore, and now we have effectively extracted the result and the times. So we're not going to do any of this again, but we are going to. Okay, elapsed time. Got to concatenate that string with show of dt. But the problem is the binding of this is going to bind the function call to that first string as the parameter. So we either have to bracket that whole tail, or again we use the $sign trick. So correctness goes into primary tests, so that's this guy. Timed tests, we have to uncomment. We're no longer doing this thing. What we are is timing. To make timing. Here we go. Okay, that didn't quite compile, but that's okay. What are we doing here? So couldn't match expected type with IO, etc., etc., etc. So what do we have here? We have this is what happens when your type system encompasses whether or not something's stateful. So in the expression time it, right, so where is time it? That's, I don't even know what time it is, because it's not the function I wrote. Time it. Oh, stack GSA. Interesting. I don't know where that function comes from. Because, is it, oh, yes, I do. Duh, I was looking at the C++ version of the time it function. Haha, give me a minute. I am a bit of an idiot. So we're going to go up to here, down into here, down into here, and we're going to go into source where I have my library stuff. There's the time it. So inconsistency in camel case versus everything else. So, so time it, get time, in order to get time from the clock of the universe, the computer, that has to be done basically in this I/O elevated context, the monad. I didn't want to use that, but it's done in the I/O context. And so in order to use getTime, the function itself basically has to be itself in the I/O context. What that means is that I have to getting a value through time. It requires actually executing it, not in a let statement, because let statements don't execute. It requires executing it, and that requires it not being inside the let, because this is not the way this is done. In order to do this, lets are only for pure values, even though those pure values can themselves be actions that are as yet unexecuted. But to actually execute it has to be done like this, and this has to be done like that, and I think that's sufficient. Because there we go. No, yes? Stack run. And actually what I need to do is the time tests. Oh, I already have big test, 0 timing. So there we go. Okay. Because I don't have that. Yep. Everybody paying attention? All right, so doing the short version of that test where did I actually produce the values? I might not have produced I should have produced the values. That is a really small number. That makes no kind of sense at all. Because did I do it on the short? No, I didn't. It did up to 1,000. Tricky to time Haskell stuff if you don't use the values that come out of it. So I just want to make sure. Let's actually disable the primary tests. I only want to do the primary tests, or I only want to do the time tests now. And for the sake of completeness, let's go back over here or not completeness, for unity, as it were. Let's do that. So if I do that, it evaluated that in 0.128061. Yeah, right. The problem is that in here, by the time I get to here, tries by nested loops has not been evaluated. So it could be the case that it's returning early. Sorry, it's not returning early. It's not evaluating this until here and not actually doing the timing, which means my timeit code would be broken. So let's see if we can make sure that this is not misbehaving. Because if my supposition is correct and I make this really quite large, not in the CPP file, come on, pay attention, there's a test afterward. So that's going up to 1,000. We're going to put this up to something really unreasonably big. So what should happen here is that when I run this, it should find as failed because I have not typed correctly. So in the time test, what this is going to do is it's going to that is not what I wanted to change around. What I want to change around is actually this one temporarily. If this is not being evaluated until here, then this, even on a stupidly big solution, should output a negligible amount of time, and then it should get stuck trying to resolve this in order to be able to do the printing. Which means that then I have to go and fix my timing code, which I will not do on the stream unless I can spot it really, really easily. Oh. Interesting. It actually did not do that. Interestingly, time test start, it should have tried to evaluate, like it should have gone through this code, and if this time it function that I wrote failed to properly force the evaluation before it left during the elapsed timer, then evaluating this should have been super quick, and then it should have stalled because laziness. But this is supposed to force it, like it's supposed to disable laziness effectively, and so this should have been forced while in the middle of that, while in the middle of the timing code. Then it should have dumped out the values, and then it should have shown the elapsed time. All right, let's. Okay, so I've reversed that back to normal, but I just want to quickly do a stack run again and see that it still stalls, because it should stall the same way. Could just be that the DT value that it outputs is bogus. And now we're getting a weird... Not sure why that happened. Let's just... Wow, I've been streaming for nearly 5 hours on this. While building the package, a copy failed. Let's just make sure I'm not in a really weird situation where, say, my drives have run out of space, because that would be feeble. Now, lots of free space there, although less than I'd like. That's drive C, that's fine. And drive D has lots of free space. So it's not a free space issue. Something's gotten locked down. A process has gotten locked down somehow. So let's try once again. Not my preferred way of running this, but there we go. Behave this time. Hopefully I've unhooked whatever executable might have been tying things up. So yeah, that didn't output my time tests message either. So it could just be that the time value coming out is broken for some really obscure reason. That's new. Let's try doing a more reasonable value though. Let's do 1,000. There we go. We got an elapsed time that was a little bit less stupid. All right. So that takes nearly a second to do it in Haskell. Don't know why I had all that problem. I must not have rebuilt at some point. So it takes about a second in Haskell, and if we go back to the C++ version of this, that is that still doing 1,000? It might be doing 1,000. Yes, it is. So this is giving the same. Oh, let's just double check that it is giving the same results. This is clearly not what you would call necessarily performant code, even though we've written it in a similar fashion. This is about, it's not quite 10 times slower. It's more like 8 times slower. But that's not fabulous. That could definitely be improved. Now, this isn't really, as I said, meant to be a Let's Make Haskell performant channel, but this shows that there is a way to at least start translating C++ code over to Haskell if that's the way you would approach this. I know a lot of imperative programmers probably would not or are not sort of necessarily going to gravitate toward a much more functional style. Although I think that's starting to change, what with link and hopefully with ranges in C++. So we are going to go and take this, and in the next video, because I'm kind of done for today, this has been a while, what I'm going to do is the next time I'm going to tackle taking the Haskell side of this and taking all of these functions that do sort of explicit recursion or that do things in an inefficient or non-Haskell-y way and try to find a better way to do it in order to be able to tighten this up. And especially because that's just silly. That's just plain silly. If you're doing, we obviously do have a nested loop situation here, but we can clearly come up with a better way to produce all of the necessary Python list elements, and to also, not Python list elements, all of the Pythagorean triangle list elements in a way that can be really quickly filtered. We need to turn this into a lean, mean filtering machine that does not involve explicit recursion like this, so that the compiler can find better ways to fuse the code. And we will do that next time. And then I think we'll probably, because that one's going to be quite a long, I think that one's going to be quite a long video as well. I think the one after that, I will then take the C++ code and massage it to try to use the STL, maybe ranges if I can find a compiler that can do it properly, and see if I can make it a little bit more Haskell-y and see how that affects the performance in the other direction. And writing in a functional style in a language that really doesn't support it. And that is ultimately going to be the point. When you write in a language, write in the style that the language best supports, and obviously choose a language which suits your particular problem space. But hopefully this has been a fun exploration of using two very different languages in order to be able to solve a problem. And what we have not yet seen really is how does the proper Haskell-y version of this measure up, and what does its performance characteristics look like, and is it easy to read, is it easy to understand? Join me for that in the part 2 of this particular video. I really appreciate you joining me for all of this. It's been kind of a fun experience and a diversion from just playing games on my channel, and I'll be doing more of this in amongst my my game streams. So thanks for joining me. Please join me next time, and I will see you in the next stream.